we're going to further extend our SQL statement by introducing group functions. We use group functions to obtain summary information, for example, averages, by grouping rows in a table into smaller sets. Unlike the single row functions, group functions operate on sets of rows to give one result per group. These sets may be made up of the entire table or the table that is split into groups. Looking now at the type of group functions that are available to be used in your SQL statement. The first is the average function. The average function returns the average value of n and ignores null values. The count function counts the number of rows where the expression evaluates to something other than null. Count all selected rows using the star. This includes duplicates and rows with nulls. The max function returns the maximum value of an expression and ignores null values. The min function returns the minimum value of an expression and ignores null values. The sum function sums the value of n, ignoring null values. The list_ag function orders data within each group specified in the order by clause and then concatenates the values of the measure column. The stddev function returns the standard deviation of n, ignoring null values, and the variance function. This returns the variance of n, ignoring null values. The group function is placed after the select keyword, and you may have multiple group functions separated by commas. The syntax for the group function is: specify the function, for example, count, and then in brackets you specify the keywords either distinct or all, followed by the expression. Some guidelines when using the group function. The distinct keyword ensures that the function only considers non-duplicate values. The all keyword will consider every value, including duplicates. All is the default, and if using all, you do not need to specify it in your syntax. The data types for the functions with an expression argument could be a char, a varchar2, a number, or a date. All group functions ignore null values. To substitute a value for a null value, make use of the NVL, NVL2, coalesce, case, or decode functions. We have introduced you to group functions, the types of group functions available to be used in your SQL statements, and the syntax for the group function. In this video, we will learn how to use the average and sum functions to group numeric data in a SQL statement. The average function returns the average value of an expression. This function takes an argument of any numeric data type or any non-numeric data type that can be implicitly converted to a numeric data type. The sum function returns the sum of values of an expression and can be used as an aggregate or analytic function. It takes an argument of any numeric data type or any non-numeric data type that can be implicitly converted to a numeric data type. In this slide, we show an example displaying the average, the highest, the lowest, and the sum of monthly salaries for all sales representatives. Let's go to SQL Developer and look at a further demonstration using the average and the sum functions. In our first SQL statement, we're going to select the average salary and the total of all salaries for all employees in the employees table. The SQL statement will look as follows. We will select, we will use the average function, and we will pass the salary column. We will give this column a heading. We will call it average salary. Next, we will use the sum function. We will pass it the salary column. And again, we will give this column a heading. We will call it total salary. We're selecting from the employees table. Let's review the output of this SQL statement. In the query result, we can see one line is returned. The average salary returns the average salary across all employees in the employees table, and the total salary returns the total salary for all employees in the employees table. Next, we're going to extend our SQL statement to add in the round function, as we would like to pass only 2 decimal places. We add in round. We include it around our average function. We specify 2 decimal places. Let's execute the statement to ensure it is displayed correctly. We can see our average salary now returns in 2 decimal places. Next, we're going to extend this SQL statement as we would like to see the average salary grouped by manager. To do this, we will add the manager column in. As we are grouping by manager ID, we will need to add in the group by clause, and we're going to group by manager ID. And for the purpose of this exercise, we're going to sort the data by the manager ID. Let's execute the statement. In our query result, we have the manager ID column with a list of all manager IDs. We have the average salary. So this is the average salary for the employees for manager 100. And in the total salary column, this is a sum of all the salaries for the employees who have a manager ID of 100. You are now ready to use the average and the sum functions to group numeric data in a SQL statement. The min and max functions are used to group numeric, character, and date data types in a SQL statement. The min function returns the minimum value of an expression and can be used as an aggregate or analytic function. The max function returns the maximum value of an expression and can be used as an aggregate or analytic function. The example in the slide displays the minimum and maximum values for the hire date in the employees table. The minimum value is the date that the first employee was hired, and the maximum value is the date that the last employee was hired. In this example, we've used the date data type. Note, the average, sum, variance, and standard dev functions can be used only with numeric data types. The min and max functions cannot be used with a lob or long data type. Let's go to SQL Developer now, and we'll demonstrate an example using a numeric and a character data type. In our first SQL statement, we're going to demonstrate the numeric data type. We would like to see the lowest and the highest salaries for all employees. The SQL statement will look as follows. We will specify the min function and the salary column. Next, we specify the max function and we specify the salary column. We're selecting from the employees table. We execute our SQL statement. In the query result, we can see the minimum salary, so this is the person that earns the lowest salary in the employees table, and the max salary, the person that earns the highest salary in the employees table. Next, we're going to select the minimum last name and maximum last name from the employees table to demonstrate the character data type. The SQL statement will look as follows. We select min, last name, max, last name from employees. The query result displays the employee's last name that is first and the employee's last name that is last in an alphabetical list of all employees. You are now ready to use the min and max functions to group numeric, character, and date data types in a SQL statement. In this video, we're going to learn how to use the count function in a SQL statement. The count function has three formats: count star, count expression, and count distinct expression. Count star returns the number of rows in a table that satisfy the criteria of the select statement, including duplicate rows and rows containing null values in any of the columns. If a where clause is included in the select statement, count star returns the number of rows that satisfy the condition in the where clause. The example in the slide displays the number of employees in Department 50. In contrast, count expression returns the number of non-null values that are in the column identified by the expression. In the example in the slide, we display the number of employees in Department 50 who can earn a commission. The count distinct expression returns the number of unique, non-null values that are in the column identified by expression. Use the distinct keyword to suppress the counting of any duplicate values in a column. The example in the slide displays the number of distinct department values that are in the employees table. We are in SQL Developer, and we will demonstrate each of the three count function formats. First, we're going to select a count of all employees in the employees table. We select count star from employees. We execute this SQL statement. The query result returns the count of the number of rows in the employees table. Next, we're going to select a count of the IT programmers in the employees table. The SQL statement will look as follows. Select count. We specify the job ID column from employees where job ID is equal to IT_prog. We execute the statement. In the query result, we can see there are 5 employees with a job ID of IT_prog. Lastly, we're going to do a select count distinct. On manager ID, we would like to see a count of the managers that exist in the employees table, a distinct list. We select count, we specify the distinct keyword, and we specify the manager ID column. We're selecting from the employees table. Let's execute this statement and review the output. In the query result, we can see that there are 18 distinct manager IDs that exist in the employees table. In this video, we've covered the count function and the three formats available for the count function. You are now ready to use the count function in your SQL statements. Working with null values when grouping a set of rows in a SQL statement. By default, all group functions ignore null values in the column. We can, however, use the NVL function to force group functions to include null values. In the first example in the slide, the average is calculated based only on those rows in the table in which a valid value is stored in the commission percent column. The average is calculated as the total commission that is paid to all employees divided by the number of employees receiving commission. In the second example, where we include the NVL function, the average is calculated based on all rows in the table, regardless of whether null values are stored in the commission percent column. The average is calculated as the total commission that is paid to all employees divided by the total number of employees in the company. To demonstrate how null values impact the group functions in the result of a SQL statement, I'm going to demonstrate the same query that was in the slide. First, we're going to do a count of all employees in our table. We have 108 employees in the employees table. Next, we're going to count how many employees receive a commission in the employees table. A SQL statement where commission percent is not null. Let's execute this statement. In the query result, we can see there are 35 employees that receive a commission. Now let's execute the statement containing the average function. In the result, where we've specified only the average function and it's based on the commission percent column, the output returns a value of 0.22. So this is an average across the employees who receive a commission. Next, we'll include the NVL function. The query now will evaluate all rows in the table, irrespective of whether their commission percent contains a value or not. Let's execute this statement. In the query result, we can see that the output is now 0.07. This is due to the average being calculated across all employees in the table, irrespective of whether their commission percent contains a value or a null. You can see from the examples, the null values in a column can impact the output result of a SQL statement. In this video, we're going to look at how to divide rows in a table into smaller groups and look at how we extend the syntax of the SQL statement to include the group by clause. Up to this point, all group functions have treated the table as one large group of information. You may, however, need to divide the table of information into smaller groups, and this can be done using the group by clause. In the example in the slide, we would like to see the average salary per department. Previously, we viewed the average salary for all employees in the table. We can now view the average per department by including a group by clause in our SQL statement. The group by clause can be used to divide the rows in a table into groups, and you can then use the group functions to return summary information for each group. Looking now at the syntax for the group by clause, we specify the group by keyword followed by the group by expression. The group by expression specifies the columns whose values determine the basis for grouping rows. Some guidelines when using the group by clause. If you include a group function in a select clause, you cannot select individual columns as well, unless these individual columns appear in the group by clause. You receive an error message if you fail to include the column list in the group by clause. You can use a where clause to exclude rows before dividing them into groups. You can substitute columns with an expression in the select statement, and you must include the columns in the group by clause. A column alias cannot be used in the group by clause. In future topics, we will learn how to use the group by clause in our SQL statement, further extend the group by clause to include multiple columns, and we will learn how to identify illegal queries when using the group by clause. In this video, we have introduced how to group data in a table into smaller sets. In this video, we're going to learn how to use the group by clause in a SQL statement. When using the group by clause, make sure that all columns in the select list that are not group functions are included in the group by clause. The example in the slide displays the department number and the average salary for each department. The select statement is evaluated as follows. The select clause specifies the columns to be retrieved, the department number column in the employees table, and the average of all salaries in the group that you specified in the group by clause. The from clause specifies the tables that the database must access, in this case, the employees table. The where clause specifies the rows to be retrieved. As there is no where clause, all rows are retrieved by default. The group by clause specifies how the rows should be grouped. The rows are grouped by department number, The average function that is applied to the salary column calculates the average salary for each department. To order the query results in ascending or descending order, include the order by clause in the query. The group by column does not have to be in the select clause. For example, the select statement in the slide displays the average salary for each department without displaying the respective department numbers. Without the department numbers, however, the results are not meaningful. You could also use the group function in the order by clause. Let's go to our SQL Developer session and write a SQL statement using the group by clause. For our first query, we're going to select the number of employees per manager. Our SQL statement, we will select the manager ID column and we will use the count function. We're selecting from the employees table and we're going to group by manager ID. We will include the order by clause in our statement and we're going to sort it by the manager ID. Let's execute this statement and review the output. In the query result, we have returned the manager ID column with a count of the number of employees per manager ID, and the data is sorted by the manager ID column. Let's now further extend this SQL statement to include the minimum and maximum salaries per manager ID. To do this, we will add in the minimum function. We will specify min and the salary column, and we will include max and the salary column. We are selecting from the employees table. We're still grouping by our manager ID, but now we will order our data by the minimum salary. So we will include our minimum function. Let's execute this statement. In the query result, we have the manager ID. We have a count of the employees per manager ID. We display the minimum salary value per manager and the maximum salary value per manager. Our data is sorted by the minimum salary value. You are now ready to use the group by clause in your SQL statements to group data into smaller sets. Using the group by clause on multiple columns in a SQL statement. We group by multiple columns when we need to see results for groups within groups. In the example in the slide, the output on the left shows all rows in the employees table, displaying the columns department ID, job ID, and salary per employee. The output on the right shows an example of grouping within a group. We first group the rows by department ID and then further group the rows by the job ID. The output result is the sum of the salary per department and job ID combination. The data on the left shows 4 stock clerks in Department 50, and we display the salary for each clerk. On the right, we display the sum of the salary for the 4 stock clerks in Department 50. We have done this by grouping the data by the 2 columns, Department ID and Job ID. The syntax for grouping multiple columns. We specify the columns in the group by clause in the SQL statement. The group by clause groups rows but does not guarantee the order of the result set. To order the groupings, we need to use the order by clause. In the example in the slide, the select statement contains a group by clause, and it is evaluated as follows. The select clause specifies the columns to be retrieved. We are selecting the department ID, the job ID, and the sum of all salaries in the group specified in the group by clause. The from clause specifies the tables that the database must access. In this case, we are selecting from the employees table. The where clause reduces the result set to return only those rows where the department ID is greater than 40. The group by clause specifies how you must group the resulting rows. First, the rows are grouped by department ID. Second, the rows are grouped by the job ID in the department ID groups. The order by clause then sorts the results by department ID. Note, the sum function is applied to the salary column for all job IDs in the result set in each department ID group. Also note that the SA_rep row is not returned. The department ID for this row is null, and therefore it does not meet the where condition. Let's go to SQL Developer and demonstrate grouping based on multiple columns. To demonstrate grouping based on multiple columns, we're first going to write a select statement that will group by one column. We will then further extend our SQL statement to add in a second column. Our SQL statement will look as follows. We will select the manager ID, and we would like to see a sum of the salary per manager ID. We are selecting from the employees table. We're going to group by the manager ID column, and we will sort our data by the manager ID. Let's execute this statement and review the output. In the query result, we can see we have the sum of the salary per manager ID. To further extend our SQL statement, we would like to see a sum of the salary per manager and job title. To do this, we modify our SQL statement to add in the job ID column. We add the job ID column in the select clause, and we add the job ID column in the group by clause. Let's re-execute this statement and review its output. In the query result, we can now see the sum of the salary per job ID within the manager ID group. You have now learned how to extend your SQL statement to include groups within groups by using multiple columns in the group by clause. In this video, we're going to describe illegal queries when using the group by function in a SQL statement. Whenever we use a mixture of individual items and group functions in the same select statement, we must use a group by clause. The group by clause must specify the individual items. In the first example in the slide, the individual item would be the department ID. If the group by clause is missing, the error message, "Not a single group function," will be displayed, and an asterisk points to the offending column. The error in the first example in the slide can be corrected by adding in the group by clause. In this example, we would add in group by department ID, and this will resolve the error. Any column or expression in the select list that is not an aggregate function must be in the group by clause. In the second example in the slide, the job ID column is neither in the group by clause nor is it being used by a group function, and therefore the error, "Not a group by expression," is returned. The error in the second slide example can be corrected by adding job ID in the group by clause. A restriction when working with group functions is that the where clause cannot be used to restrict groups. The select statement in the example in the slide results in an error because it uses the where clause to restrict the display of the average salary of those departments that have an average salary greater than $8,000. To restrict the group, use the having clause after the group by clause. We will learn how to restrict group results and how to use the having clause in a future lesson. Group functions cannot be used in the where clause of a SQL statement. Let's now go to our SQL Developer session and demonstrate the errors that may be encountered when working with the group by clause in a SQL statement. In our first SQL statement, we're going to select Department ID, and we will count all the records per department ID from the employees table. If we execute this SQL statement, we encounter an error. Error-00937, not a single group function. To correct this error, we need to add in the group by clause to group by the individual item, the department ID. If we now execute this SQL statement, it executes successfully. Next, we select department ID, job ID, and sum of the salary from the employees table. And for this example, we're going to group by department ID. Let's execute this SQL statement. We can see in the query result, we encounter the error error-00979, not a group by expression. To correct this error, we need to add the job ID column into the group by clause. If we then re-execute this SQL statement, our SQL statement executes successfully. In this video, we've covered illegal queries when using group functions and described the restrictions with regards to using the where clause to restrict the data returned by groups. In this video, we're going to learn how to restrict group results in a SQL statement. The having clause is used to restrict groups in the same way you would use the where clause to restrict rows that you select. To find the maximum salary in each of the departments that have a maximum salary greater than $10,000, you need to first find the average salary for each department by grouping by department number, and then restrict the groups to those departments with a maximum salary greater than $10,000. We use the having clause to specify the groups that are to be displayed and further restrict the groups on the basis of aggregate information. In the syntax, the group condition restricts the groups of rows returned to those groups for which the specified condition is true. The steps performed by the Oracle server when using the having clause are: the rows are grouped, the group function is then applied to the group, and next, the groups that match the criteria in the having clause are displayed. The having clause can precede the group by clause, but it is recommended that you place the group by clause first, as the having clause logically follows on after the group by clause. Groups are formed and group functions are calculated before the having clause is applied to the groups in the select list. Note, the where clause restricts rows, whereas the having clause restricts the groups. In this example, we display the department number and the maximum salary for those departments with a maximum salary greater than $10,000. The group by clause can be used without using a group function in the select list. If rows are restricted based on the result of a group function, you must have a group by clause as well as the having clause. The example in this slide displays the job ID and the total monthly salary for each job that has a total payroll exceeding $13,000. The example excludes sales representatives and sorts the list by the total monthly salary. To demonstrate the use of the having clause to restrict the group results, we will write a SQL statement to select the manager and the lowest salary for employees whose manager ID is not null and where the group function have a minimum salary greater than $6,000. Our select statement, we're going to select the manager ID. Our aggregate function, we're going to select the salary from the employees table, where the manager ID is not null. We're then going to group by the manager ID. We would now like to restrict the group to a minimum salary of greater than $6,000. To do this, we include the having clause. We specify the group function, so where the minimum salary is greater than 6,000. We then order by the minimum salary in descending order. Let's execute the statement and review the output. In the query result, we have returned rows where the manager ID is not null. We have then grouped by the manager ID and returned the minimum salary where the minimum salary for the group is greater than $6,000. We can see for manager 102, the minimum salary is $9,000. And that is how we use the having clause to restrict the group results in a SQL statement. Group functions can be nested to a depth of 2 functions. In the example in the slide, the average salary for each department ID is calculated and the maximum average salary is then displayed. Note that the group by clause is mandatory when nesting group functions. We are in SQL Developer, and we are first going to look at the error encountered when nesting group functions to more than 2 levels. Our SQL statement nests 3 group functions: the count, the sum, and the average functions. If we execute this SQL statement, the following error is returned. Error 00935. Group function is nested too deeply. We can only nest group functions to a depth of 2 functions. To demonstrate the nesting of group functions, in our first SQL statement, we would like to see the average length of the first name grouped by department ID. Our SQL statement looks as follows. We select the department ID. We then select the average length of the first name. So the first name is our first name column. We're selecting the length of the first name, and we then calculate the average per department ID. We're selecting from the employees table. We group by the department ID, and we're going to sort it by department ID. Let's execute our SQL statement and review the output. In the query result, we can see we've returned per department ID the average length of the first name. Remember, when nesting group functions, the group by clause is mandatory. For our next SQL statement, we're going to select the average salary per manager ID. We will then further extend the SQL statement to calculate the maximum average salary across all managers. We will include a where clause as we want to return only rows where the manager ID is not null. Our SQL statement will look as follows. We select the manager ID and the average salary from the employees table where the manager ID is not null. We would like to return rows only where the manager ID has a value. We group by the manager ID column, and we're going to order by the average salary descending. So we would like to see the highest average salary across the manager IDs. Let's execute this statement. In the query result, we can see we return the average salary per manager ID, and the data is sorted on the average salary descending. We would now like to extend this statement We would only like to see the maximum average salary across all managers. To do this, we're going to remove the manager ID column. We include max for the maximum average salary. We're still going to select where the manager ID is not null. We're going to group by the manager ID, and we will remove the order by clause as we'll only return one value. Let's execute the statement now and review its output. In our query result, we have returned the maximum average salary across all manager IDs. Now you know how to use nested group functions in a SQL statement. Now that you've learned the basics of the group by and the having clauses to report aggregated data in your SQL statement, it's time to put that knowledge to work. In this exercise, you will write a query to display the number of people with the same job. You will generalize the query so that the user in the HR department is prompted for a job title. You will then create a report to display the manager number and the salary of the lowest paid employee for that manager. Exclude anyone whose manager is not known. Exclude any groups where the minimum salary is $6,000 or less, and sort the output in descending order of salary. When you are ready, pause this video and perform the exercise. When you are done, come back to the video and I will work through the exercise with you. We are connected to our HR connection in SQL Developer. In the first task, we're going to write a query to display the number of people with the same job. Our SQL statement will look as follows. We will select job ID and count star from the employees table, and we're going to group by the job ID. Let's execute the statement. In the query result, we've returned a count of the number of employees per job ID. For the next task, we're going to generalize the query so that the user in the HR department is prompted for a job title. To do this, we're going to add a where clause. We will specify where job ID is equal to, and we will prompt for the job title. And our job title needs to be in single quotes. Let's execute this statement and review the output. We are prompted to enter a job title. In this example, I'm going to enter the job title IT_prog. We click on the OK button, and in the query result, we can see we have 4 employees with the job ID IT_prog. For the final task, we will create a report to display the manager number and the salary of the lowest paid employee for that manager. We will exclude anyone whose manager is not known, and we will exclude groups where the minimum salary is $6,000 or less. The data will be sorted in descending order of salary. Our SQL statement will look as follows. We will select the manager ID. We will select the minimum salary from the employees table where the manager ID is not null. We will group by the manager ID, and we will include the having clause, having a minimum salary greater than $6,000. We then order by our minimum salary in descending order. Let's execute this statement. In the query result, we display the manager ID and the salary for the lowest paid employee for that manager, and only where the minimum salary is greater than $6,000. The data has been sorted by the salary in descending order. Sometimes you need to use data from more than one table. In this video, we're going to describe how to obtain data from multiple tables using joins in a SQL statement. The example in the slide displays 2 separate tables, the employees table and the jobs table. The employee ID exists in the employees table, the job ID exists in both tables, and the job title exists in the jobs table. To produce a report displaying the employee ID, the job ID, and the job title, we would need to link the employees and jobs tables to access the data from both. Joins that are compliant with the SQL 1999 standard and that can be used to join tables include natural join with the natural join clause, a join with the using clause, a join with the on clause, and the outer joins. These consist of a left outer join, a right outer join, and a full outer join. Cross joins can also be used. We will discuss each of these joins in detail in future videos. This slide demonstrates the SQL 1999 syntax used for joining more than one table together. Looking now at the syntax. In the select clause, table1.column denotes the table and the column from which the data is retrieved. The natural join joins two tables based on the same column name. The next join table 2 using column name, performs an equijoin based on the column name. Next, join table 2 on table 1.column name equal to table 2.column name, performs an equijoin based on the condition in the on clause. Left, right, full outer is used to perform outer joins. Cross join returns a Cartesian product from the two tables. Additional information regarding the types of joins can be found in the section titled Select in the Oracle Database SQL Language Reference for Database 12c. You are now ready to delve deeper into the different types of joins and learn how to use these joins in your SQL statements. Creating and retrieving records with natural joins. A natural join is used to join tables automatically based on the columns in the two tables that have matching data types and names. The natural join clause is based on all the columns that have the same column name in both tables. Rows are selected from the two tables that have equal values in all matched columns. And if the column names are the same but the data type for the columns are different, this will result in an error. The syntax for a natural join: we select from table 1, we then specify the keyword natural join, and we then specify table 2 that we are joining to. In the example in this slide, the jobs table is joined to the employees table by the job ID column. The job ID column is the only column with the same name in both tables. If other common columns were present, the join would have used them all. Additional restrictions on a natural join are implemented by using a where clause. An example of this would be if we included a where clause to limit the department ID where the department ID is in 20 and 50. Let's go to our SQL Developer session and demonstrate how to use natural joins in our SQL statements. We need to create a report to view the departments and include the city where these departments are located. The two tables that we're going to be working with are the departments table and the locations table. I'm first going to do a describe on these two tables for us to see which of the columns that match. We describe departments. In our departments table, we have a department ID, the department name, the manager ID, and the location ID. Let's now do a describe on the locations table. In our locations table, we have the location ID. We can see that the location ID in the locations table matches to the location ID by column name and data type in the departments table. We are now going to write our SQL statement, and it will look as follows. We're going to select the department ID, the department name, the location ID, and the city. From the departments table, we then specify our natural join to join to the locations table. Let's execute the statement and review the output. In the query result, we display the department ID, the department name, the location ID, and the city where the department is located. The location ID is the column that is common to both the departments and the locations tables, and it is used to join the two tables together. Let's extend our SQL statement and limit the departments that we view in the output. We include a where clause, where department ID is in 20 and 50. We would like to see the output only for those two departments. We execute this SQL statement, and in the query result, only the records for the departments 20 and 50 are returned. You are now ready to join two tables using the natural join in your SQL statements. In this video, we're going to learn how to join tables with the using clause. Natural joins use all columns with matching column names and data types to join the tables. The using clause can be used to specify only those columns that should be used for an equijoin. If several columns have the same name but the data types do not match, use the using clause to specify the columns for the equijoin. The using clause is used to match only one column when more than one column matches. To determine an employee's department name, you compare the department ID column values in the employees table with the department ID values in the departments table. The relationship between the employees and departments tables is an equijoin. This means that the values in the department ID column in both tables must be equal. Frequently, this type of join will involve primary and foreign key constraints. In the from clause, we specify the join clause and include the column that we are joining the two tables on. In the slide, we specify from the employees table, join departments table using the department ID column. The example in the slide, the department ID columns in the employees and department tables are joined, and we are therefore able to view the location ID of the department where the employee works. The HR department needs a report of all employees with corresponding departments. We are going to write a query to display the last name, department number, and department name for all employees. Our SQL statement will look as follows. We select last name, department ID, and department name. From, we specify our first table, that's the employees table. We then join on the departments table, and we specify our using keyword. We will join based on the department ID, where the department ID value is equal in both the employees and the departments table. Let's execute this statement and review the output. In our query result, we display the last name from the employees table. We view the department ID, which is equal between the employees and the departments table. And we view the department name from the departments table. Next, we're going to write a query to display the employees' names, their job ID, and job titles. We'll do this only for the employees in departments 10, 20, 30, and 40. Let's write this SQL statement. We select the first name, the last name, the job ID, and the job title. We select from the employees table, we join to the jobs table, and we specify our using keyword. We're going to join based on the job ID column. The job ID column must be equal between the employees and the jobs table. And for this SQL statement, we'll include a where clause where department ID is in 10, 20, 30, and 40. Let's execute this statement now. In our query result, we return the first and the last name from the employees table. We return the job ID, which is the column that is equal between the two tables. And we return the job title. This column comes from the jobs table. You are now ready to join tables containing an equijoin relationship by using the using clause in your SQL statement. In this video, we're going to look at using table aliases in our SQL statement and the use of the table alias when working with the using clause. When we join two or more tables, we need to qualify the names of the columns with the table name to avoid ambiguity. Without the table prefixes, the department ID column in the select list could be from either the departments table or the employees table. It is necessary to add the table prefix to execute your query. If there are no common column names between the two tables, there is no need to qualify the columns. Using the table prefix increases the speed of parsing the statement. This is because you tell the Oracle server exactly where to find the columns. Qualifying column names with table names can be time-consuming, particularly if the table names are lengthy. Instead, you can use table aliases. Just as a column alias gives a column another name, a table alias gives a table another name. Table aliases help to keep the SQL code smaller and therefore use less memory. The table name is specified in full, followed by a space, and then the table alias. As an example, the employees table can be given an alias of an E, and the departments table an alias of D. We use column aliases to distinguish columns that have identical names but reside in different tables. Some guidelines when working with table aliases. Table aliases can be up to 30 characters in length, but shorter aliases are better. If a table alias is used for a particular table name in the from clause, that table alias must be substituted for the table name throughout the select statement. Table aliases should be meaningful, and they are only valid for the current SQL select statement. When joining with the using clause, you cannot qualify a column that is used in the using clause itself. Furthermore, if that column is used anywhere in the SQL statement, you cannot alias it. For example, in the query mentioned in the slide, you should not alias the location ID column in the where clause, because this column is used in the using clause. The columns that are referenced in the using clause should not have a qualifier, that is a table name or an alias, anywhere in the SQL statement. Columns that are common in both tables but not used in the using clause must be prefixed with a table alias. Otherwise, you will get the column ambiguously defined error. Let's go to our SQL Developer session, and I will work through the syntax of a SQL statement using a column alias and the using clause. In our SQL worksheet window, we have our SQL statement. First, in the from clause, we specify the locations table. We've given our locations table an alias called L. We join the locations table to the departments table, and the departments table is given an alias D. We're joining using the location ID. As we have the location ID specified in the using clause, when we use location ID, in the where clause, we cannot prefix it with the alias. If we look now at our select clause, we select city and we've prefixed it with an L, which references our locations table. We then select department name, and we've prefixed our department name with a D. The D is the alias for the departments table. Let's execute this statement to ensure that it executes successfully. The city and the department name for location ID 1400 is returned. In this video, we've covered table aliases and the use of table aliases when using the using clause in your SQL statement. In this video, we're going to learn how to use the ON clause to specify join conditions in the where clause in a SQL statement. The natural join condition is an equijoin of all columns with the same name between two tables. We use the ON clause to specify arbitrary conditions or specify the columns that we would like to use to join the tables on. The join conditions are separated from other search or filter conditions in the where clause. By using the ON clause, the code is easy to understand. In this example, the department ID columns in the employees and department tables are joined using the ON clause. Wherever a department ID in the employees table is equal to a department ID in the departments table, the row is returned. Table aliases are necessary to qualify matching column names. The ON clause can also be used to join columns that have different names. The parentheses around the joined columns, as in the example, where E.departmentID is equal to D.departmentID, is optional. If we had to omit the parentheses, the query would still work. Note, when you use the execute statement icon to run the query, SQL Developer suffixes an _1 to differentiate between the two department ID columns. To demonstrate how to retrieve records with the ON clause, our SQL statement lists the address of each office, including the country where the office is located. Our data will be sorted by the country. Looking now at our SQL statement, we are selecting from the locations table. We've given our locations table an alias called L. We then join to the countries table, which has an alias of a C. We are joining on the country ID, so where the country ID in the locations table is equal to the country ID in the countries table. Our data is sorted by the country name and the city. The columns that we're selecting, we select the country name from the countries table, the country ID column from both the locations table and the countries table, and we then return the location ID, the street address, the city, and the postal code from the locations table. If we now execute the SQL statement, in the query result, the rows returned include the country per location where the country IDs match between the two tables, and the address for each location is returned. For example, country Canada, we can see that 2 rows are returned as there are 2 entries in the locations table where the country ID is equal to Canada, the city Toronto, and Whitehorse. You are now ready to make use of the ON clause to specify join conditions in the where clause in a SQL statement. Using a 3-way join to join 3 tables in a SQL statement. There may be instances where the information that you need to extract from the database exists in multiple tables. In this video, we're going to look at extending our SQL statement from joining 2 tables to now joining 3 tables together. In the example in the slide, The first join to be performed is the employees table joined to the departments table. The first join condition can reference columns in the employees and departments tables and cannot reference columns in the locations table. The second join condition, joining to the locations table, can reference columns from all three tables. Let's now go to our SQL Developer session, where we will first demonstrate how this SQL statement in the slide can be written in two different ways. We will then write a SQL statement joining three columns. In our SQL Developer SQL Worksheet window, we have two SQL statements that return exactly the same output. In our first SQL statement, this is the statement that was displayed in the slide. We join between the employees, departments, and locations table using the ON clause. The second SQL statement, we use the using clause. We specify the columns that we are joining on between the two tables. Let's execute our statements to review their output. For the first SQL statement, we're able to see we have 3 executives in Seattle. Let's execute the second statement and review its output. We can see in the query result that exactly the same information is returned using a different format for our SQL statement. This demonstrates that there is more than one way in which you can write your SQL statement and return the correct output. Now, to demonstrate a three-way join, our report should display the department name, the city where the department is located, and the country. We will first create a SQL statement joining two tables together to display the department and the location per department. We will then extend the SQL statement to add in the third table, the countries table. Our SQL statement will look as follows. We're going to select the department name from the departments table, and we're going to select the city from the locations table. So we're selecting from departments. We give our departments table an alias D. We then join to the locations table, and our locations table alias is an L. And we're going to use the using clause, and we're going to join on the location ID. Let's execute our statement to ensure that it executes successfully. In our query result, we can see we return the department name and the city where that department is located. Next, we're going to extend our SQL statement to add in our third table. To do this, we're going to add in the join. We're going to join to the countries table. We give our countries table an alias C, and we're going to join using the country ID column. The join is between the countries table and the locations table. To demonstrate the output, in our select clause, we're going to add in the country. Let's execute our SQL statement now. In the query result, we can now see that the output is now returning the country name per city per department name. This is how we use a three-way join to join three tables in a SQL statement. In this video, we're going to look at applying additional conditions to a join. We make use of the AND or the WHERE clause to apply additional conditions. The examples shown in the slide perform a join on the employees and departments tables, and in addition display only employees who have a manager ID of 149. The first SQL statement displays an example of how to add additional conditions to the ON clause by including the AND clause. Alternatively, The second SQL statement displays an example of how to use a where clause to apply additional conditions. Both of these queries produce the same output. To demonstrate the use of the AND or where clauses to apply additional conditions to a join, we would like to view all departments located in Seattle. To do this, our SQL statement will look as follows. We select the department name, the location ID, and the city. From the departments table, we specify the alias D for the departments table. We then join to the locations table. The locations table has an alias of L. We join on the location ID in the departments table where it is equal to the location ID in the locations table. We then add an additional condition. We would like to see only records where the location ID is equal to 1700. Let's execute this SQL statement and review the output. In the query result, the rows returned are a list of all department names located in Seattle. To demonstrate the use of the where clause to apply an additional condition to the join, we will modify our SQL statement. We replace the AND keyword with the where clause keyword. If we execute this SQL statement now, in the query result, the rows returned are exactly the same as the rows returned by the first SQL statement. We've returned a list of all departments located in Seattle. You are now ready to apply additional conditions to a join in your SQL statement. Sometimes you need to join a table to itself. We use a self join to join a table to itself in a SQL statement. To find the name of each employee's manager, you would need to join the employees table to itself. For example, to find the name of Ernst manager, you need to first find Ernst in the employees table by looking at the last name column. Then find the manager number for Ernst by looking at the manager ID column. Ernst's manager number is 103. We then find the name of the manager with the employee ID 103 by looking at the last name column. Hunold's employee number is 103, so Hunold is Ernst's manager. In this process, you look at the table twice. The first time you look in the table to find Ernst in the last name column and the manager ID value of 103. The second time, you look in the employee ID column to find 103 and the last name column to find Hunold. The ON clause can be used to join columns that have different names within the same table or in a different table. The example shown is a self-join of the employees table based on the employee ID and manager ID columns. In the from clause, we specify the employees table twice. The first reference to the employees table, we give the table name an alias worker. We then join to the employees table, giving it an alias manager. The columns that we join on in the worker table, we use the manager ID column. And in the manager table, we use the employee ID column for the self-join. The select clause lists the column depending on whether it should come from the first reference of the table, the worker alias, or the second reference, the manager alias. Let's go to our SQL Developer session, where we will amend this SQL statement to demonstrate information that can be retrieved using this self-join statement. Our first SQL statement in the SQL Worksheet window is the SQL statement from our presentation slide. We're going to select the worker last name and the manager last name from the employees table, defined with the worker alias, joined to the employees table with the manager alias. Our join is on the worker.managerID, where it is equal to the manager.employeeID. Let's execute this statement and review its output. In the query result, the last name for each employee is returned, including the last name for the manager per employee. In our next SQL statement, we have amended the SQL statement as we would like to see a list of the distinct manager IDs and their last names. Our SQL statement was amended. We've included the distinct keyword. We are now selecting the employee ID from the manager table and the manager last name. The from and on clause remain the same. We've included an order by clause. We're going to sort our rows by the manager's last name. Let's execute this statement. In our query result, we can see that we've returned 18 rows. We have the manager employee ID and the manager's last name. This is a distinct list of all the managers. For our last SQL statement, we would like to restrict the results returned by the SQL statement to return only a list of employees for manager ID 103. We would like to see the last name for the employees and the manager. In our SQL statement, we select the worker last name, the manager's last name. We're selecting from the employees table, giving it an alias worker. We are joining on the employees table, and we are giving this table the alias manager. We are joining where the worker manager ID is equal to the manager employee ID. We've included a where clause as we would like to return the rows where the manager employee ID is equal to 103. We've then ordered our data to be sorted by the last name of the employees. Let's execute this statement and review the output. In the query result, we can see we have 4 employees that report to manager 103, and we've returned the employee's last name and the manager's last name. You are now ready to join a table to itself by making use of a self-join in a SQL statement. Using a join condition containing a non-equijoin in a SQL statement. A non-equijoin is a join condition that contains something other than an equality operator. The relationship between the employees table and the job grades table is an example of a non-equijoin. The salary column in the employees table ranges between the values in the lowest cell and highest cell columns of the job grades table. Each employee can therefore be graded based on their salary. The relationship is obtained using an operator other than the equality equal to operator. The example in this slide creates a non-equijoin to evaluate an employee's salary grade. The salary must be between any pair of the low and high salary ranges. It is important to note that all employees appear exactly once when this query is executed. No employee is repeated in the list. There are 2 reasons for this. The first, none of the rows in the job grades table contain grades that overlap. That is, the salary value for an employee can lie only between the low salary and high salary values of one of the rows in the salary grade table. The second reason, all of the employees' salaries lie within the limits provided by the job grade table. That is, no employee earns less than the lowest value contained in the lowest cell column or more than the highest value contained in the highest cell column. Note, other conditions such as less than or less than and equal to and greater than or greater than and equal to can be used. But the between condition is the simplest. You need to remember to specify the low value first and the high value last when using the between condition. The Oracle server translates the between condition to a pair of AND conditions. Therefore, using between has no performance benefits, but should be used only for logical simplicity. Table aliases have been specified in the slide example for performance reasons, not because of possible ambiguity. To demonstrate retrieving records using a non-equijoin, we would like to select the last name and hire date of all employees that were hired after the employee Davis. We are first going to select the hire date for the employee Davis. This is to ensure that when we execute our SQL statement, we can validate the information returned is correct. We're selecting the last name and hire date from the employees table where the last name equals Davies. In the query result, Employee Davis was hired on the 29th of Jan 2005. For our next SQL statement, we're going to select the last name and hire date for all employees from the Employees table. We have given the table an alias E. We then join to the Employees table and have given this table an alias Davies. In the on clause, we specify where Davies.lastName is equal to Davies. There will be one row returned from the alias table Davies. Our join condition then includes a where clause, where Davies.hiredate is less than E.hiredate. In other words, return the last name and hire date for all employees whose hire date is greater than the hire date for employee Davies. Let's execute this statement and review the output. In the query result, all employees with a hire date greater than 29 January 2005 have been returned. In this video, we've covered how to retrieve records in your SQL statement using a non-equijoin. In this video, we're going to learn how to identify records not returned when an equijoin is used and when there is no direct match in a SQL statement. When a row does not satisfy a join condition, the row does not appear in the query result. In the slide example, a simple equijoin condition is used on the Employees and Departments tables to return the result on the right. The results set does not contain Department ID 190. This is because there are no employees with that department ID recorded in the Employees table. In addition, the results set does not contain the employee with the last name of Grant. This is because this employee does not have a department ID assigned in the Employees table. To return the department record that does not have any employees or employees that do not have an assigned department, you can use an outer join. Let's go to our SQL Developer session, and we will write a series of SQL statements to identify and review the rows that are not returned by a simple equijoin statement. We know that rows that do not satisfy a join condition do not appear in the query result. To demonstrate this, we're first going to select from the Employees table where the department ID is null. The query result displays that employee ID 178 with the last name Grant does not have a department ID assigned. To demonstrate where employee ID 178 is not returned in a SQL statement, where we use a simple equijoin between the employees and the departments table, we're going to select the employee ID, the last name, the department ID from the employees table. We join to the departments table, and we're joining where the department ID in the employees table is equal to the department ID in the departments table. We've included a where clause. We would like to return only the rows for employees whose last name starts with a capital G. We are sorting our data by last name. Let's execute this statement. In the query result, we can see that employee 178 with the last name Grant is not returned in the output. Next, we're going to demonstrate where a department is not returned when using a simple equijoin between the employees and the departments table. In our first statement, we will select all the departments from the departments table. The department that we are interested in is Department 190, with the department name Contracting. Next, we're going to select from the Employees table to identify if there are any employees with Department ID 190 assigned. In our query result, we can see that no rows are returned. Therefore, in our Employees table, no employees have Department 190 assigned to them. We are now going to execute our simple equijoin statement, We are selecting the employee ID, last name, and department ID from the employees table. We are joining to the departments table, and we're going to join where the department ID in the employees table is equal to the department ID in the departments table. We are then going to sort our data by department ID descending. Let's execute this statement and review the output. As we've sorted our data by department ID descending, we can see that there are no records returned with department ID 190. In future videos, we will learn about each of the different types of outer joins to return rows with no direct match in a SQL statement. In this video, we will describe the differences between an inner and an outer join. Joining tables with the natural join, using, or on clauses results in an inner join. Where the values on the join column do not match between the two tables, these unmatched rows are not displayed in the output. To return the unmatched rows, you can use an outer join. An outer join returns all rows that satisfy the join condition and also returns some or all of those rows from one table for which no rows from the other table satisfy the join condition. There are three types of outer joins in a SQL statement. A left outer join. The left outer join returns all the rows from the table on the left, even if there is no match in the table on the right. A right outer join. The right outer join returns all the rows from the table on the right, even if there is no match in the table on the left. A full outer join. The full outer join returns all the rows from the table on the left, even if there is no match in the table on the right, and returns all the rows from the table on the right, even if there is no match in the table on the left. You have now learned the difference between an inner and an outer join, and we have described the types of outer joins we can use in our SQL statements. Using a left outer join in a SQL statement. An outer join returns all rows that satisfy the join condition and also returns some or all of those rows from one table for which no rows from the other satisfies the join condition. A left outer join is used to join two tables in which all the rows are returned from the table defined on the left and only the information for the rows where there is a match in the table on the right. The left outer join syntax is used to join these tables. The plus sign is the outer join operator and can also be used to join tables. In this video, we are going to use the left outer join syntax. The query in the slide retrieves all the rows in the employees table, which is the table on the left, even if there is no match in the departments table, the table on the right. We are logged into our HR connection in SQL Developer. In order to demonstrate the left outer join between the employees and the jobs table, I updated the employees table to allow null values on the job ID column. I then updated the employee IDs 105 and 125 and set their job ID equal to null. Our SQL statement will look as follows. We will select the employee ID, the employee's last name, and the employee's job ID from the employees table. We will then select the job ID and the job title from the jobs table. We select from employees. We give our employees table an alias E. We then specify left outer join. We join to our jobs table and we give it an alias of a J. We are joining on the job ID column between the employees table and the jobs table. To reduce the number of rows returned in the output, I'm going to include a where clause to limit the number of employee IDs that we will return. And lastly, we will sort our data by the employee ID. Let's execute our statement and review the output. In the query result, where the employee had a valid job ID, we can see the job ID and the job title from the jobs table is returned. Where the employee did not have a job ID in the employees table, we can see that no job ID or job title is returned from the jobs table. You are now ready to use a left outer join in your SQL statements. Using a right outer join in a SQL statement. As with the left outer join, where all the rows are returned for the table on the left, so with the right outer join, all rows from the table on the right are returned, and only where the rows match between the two tables is the data returned for the table on the left. The right outer join syntax is used to join these tables. The query in the slide retrieves all the rows from the departments table, which is on the right, even if there is no match in the employees table. To demonstrate a right outer join, we are logged into our HR connection in SQL Developer. First, I needed to add a row into the jobs table. To do this, I used the insert statement, insert into jobs, and I specified the values for the row. Once I had inserted the row, I issued the commit statement to ensure that the data was committed into the table. Now, to demonstrate a right outer join, our SQL statement will look as follows. We will select the last name from the employees table, the job ID from the employees table. We will then select the job ID from the jobs table, and we will select the job title from the jobs table. We select from the employees. We pass the alias E for our employees table. We then specify right outer join, and we join to our jobs table, which has an alias of J. We're joining on the columns E dot job ID, where it is equal to the job ID in the jobs table. Let's execute this statement and review its output. In the query result, we can see all rows are returned from the jobs table, and where the job ID does not exist in the employees table, the data is returned from the jobs table, and the column values returned from the employees table are null. You now know how to use a right outer join in your SQL statement. Using a full outer join in a SQL statement. A full outer join is used to join two tables in which all the rows are returned from the table defined on the left, even if there is no match in the table on the right. And it returns all rows for the tables defined on the right, even if there is no match in the table on the left. The syntax used to join these tables is the full outer join syntax. The query in the slide retrieves all rows in the employees table, even if there is no match in the departments table. It also retrieves all rows in the departments table, even if there is no match in the employees table. To demonstrate a full outer join, we are logged into our HR connection in SQL Developer. We are going to join the employees table and the jobs table using a full outer join to retrieve all the rows from both tables. Our SQL statement looks as follows. We're going to select the last name from the employees table. We will select the job ID from the employees table. We will then select the job ID from the jobs table, and we will select the job title from the jobs table. We select from employees table. We give it the alias of an E. We then specify full outer join. We join to our jobs table, giving it an alias of J. The columns that we join on from our employees table, we join on the job ID, where it is equal to the job ID in the jobs table. To limit the rows that are returned in this SQL statement, I'm going to include a where clause, where the last name starts with a capital A, or where the job ID in the jobs table starts with a capital AD. Let's execute our statement and review the output. In the query result, the row for employee Austin demonstrate the row returned for a left outer join. The record exists in the employees table and not in the jobs table. If we look now at the job ID AD_manager, we can see a right outer join. The record exists in the jobs table, but not in the employees table. In a full outer join, both results are returned. You are now ready to use the full outer join in your SQL statement. In this video, we're going to describe a Cartesian product. A Cartesian product is returned by a SQL statement which contains multiple tables and in which no join condition has been defined. A Cartesian product is a join of every row in one table to every row in another table. A Cartesian product tends to generate a large number of rows, and the result is seldom useful. When writing a SQL statement containing multiple tables, you should therefore always include a valid join condition unless you have a specific need to combine all rows from all tables. Cartesian products are useful for testing. For example, when you need to generate a large number of rows to simulate a reasonable amount of data. A Cartesian product is generated if a join condition is omitted. In the example in the slide, we display the employee's last name and the department name from the employees and departments tables. Because no join condition was specified, all 20 rows from the employees table are joined with all 8 rows in the departments table, thereby generating 160 rows in the output. We are connected to our HR connection in SQL Developer. To demonstrate a Cartesian product, we're going to write a SQL statement selecting from the employees and the jobs tables. Our SQL statement will look as follows. We will select the last name from the employees table and the job title from the jobs table. We specify from employees table and from the jobs table. Let's execute this statement and review the output. In the query result, we can see that every row from the employees table is joined to every row in the jobs table. In this video, we've covered a Cartesian product which is created when specifying multiple tables in a SQL statement and by omitting the join condition. Creating cross-joins in a SQL statement. A cross-join is a join operation that produces the Cartesian product of two tables. It is good practice to explicitly state cross-join in your select statement when you intend to create a Cartesian product. It is then very clear that you intend for this to happen, and it is not the result of missing joins. The example in the slide produces a Cartesian product of the employees and departments tables. We are logged into our HR connection in SQL Developer. To demonstrate the use of the cross-join syntax when writing a SQL statement to produce a Cartesian product, our SQL statement will look as follows. We will select last name, job title, from the employees table. We then specify the syntax cross-join onto the jobs table. Let's execute this statement. When we execute this SQL statement, we can see that a Cartesian product is returned. In the query result, we can see that every row in the employees table is joined to every row in the jobs table. By including the cross-join syntax in our statement, anyone who looks at this SQL statement will know that we intended for this Cartesian product to occur. You have now learned how to use the cross-join syntax in a SQL statement when you intend to create a Cartesian product. Now that you've learned how to use joins to join multiple tables together in your SQL statement, it is time to put that knowledge to work. In this exercise, you will need to write SQL statements using joins to return data for the following reports. Write a query for the HR department to produce the addresses of all the departments. Use the locations and countries tables. Show the location ID, street address, city, state or province, and country in the output. Use a natural join to produce the results. Next, create a report to display employees' last names and the employee numbers, along with their managers' last names and manager numbers. Label the columns employee, emp number, manager, and manager number respectively. Lastly, modify the above SQL statement to display all employees, including King, who has no manager. Order the results by employee number. When you are ready, pause this video and perform the exercise. When you are done, come back to the video and I will work through the exercise with you. To perform these exercises, we are connected to our HR connection in SQL Developer. For the first task, we will write a query to produce the addresses of all departments. We will use the locations and countries table, and we will use a natural join to produce the results. Our SQL statement will look as follows. We will select the location ID, the street address, the city, state, province column, and the country name column. From the locations table, we will then specify natural join onto the countries table. Let's execute this statement. In the query result, we've returned the location ID, the street address, the city, the state or province, and the country name. We have done this using a natural join between the locations and the countries tables. For this next task, we need to create a report to display the employees' last names and employee numbers, along with their managers' last names and managers' numbers. We will be doing a self-join on the employees table, and we've given our tables an alias. Our SQL statement will look as follows. We will select, we specify the alias for the first table, the last name, and we'll specify the alias W when we select the employee ID. We're then going to select from the second table, which is an alias of M. We'll specify the last name and the employee ID. I need to add in column aliases. For our first column, we'll give it an alias of employee. We give the employee ID column an alias of emp number. We will give the manager's last name the alias of manager, and the manager's employee ID of manager number. We are selecting from the employees table, and we specify a W for the first table. We then join to the employees table, and we specify M for the second alias. We are joining on where w.managerID in the first table is equal to the employee ID in the second table. Let's execute this statement and review its output. In the query result, we've returned a list of all employees who have a valid manager ID in the manager ID column, and we've included the manager's last name and manager number where the rows are equal. We're now going to update this SQL statement as we would like to see a list of all employees, even if their manager ID is null. For this, our last task, as we would like to see all employees, irrespective of whether they have a manager ID assigned, we're going to update our SQL statement to include a left outer join, and we needed to sort our data by the employee number. We will include an order by and number 2. We're going to sort the data by the employee ID. Let's execute this statement now. In the query result, we can see that we've now returned employee King. Employee King does not have a manager ID in the employees table. And by changing our query to a left outer join, we've returned all employees and only the managers where it's relevant. In this video, you will learn how to use a subquery to solve a problem in a SQL statement. Suppose you want to write a query to find out the names of all employees who were hired after employee Davies. To solve this problem, you will need two queries. One query to find when Davies was hired, and the second query to find out who was hired after Davies. You can solve this problem by combining the two queries and by placing one query inside the other query. The inner query, it's also known as a subquery, returns a value that is used by the outer query, also known as a main query. The execution plan of the query will depend on the optimizer's decision on the structure of the subquery. A subquery is a select statement that is embedded in the clause of another select statement. They can be very useful when you need to select rows from a table with a condition that depends on the data in the table itself. The subquery can be placed in a number of SQL clauses. These include the where clause, the having clause, and the from clause. In the syntax, the operator includes a comparison condition such as a greater than sign, an equal to sign, or the in keyword. The subquery is often referred to as a nested select, subselect, or inner select statement. The subquery generally executes first, and its output is used to complete the query condition for the main or outer query. In the example in the slide, the inner query determines the hire date of the employee Davies, and the outer query then takes the result of the inner query and uses this result to display all the employees who were hired after Davies. As you can see, we can build powerful statements out of simple ones by using subqueries. We can obtain values based on an unknown conditional value from an embedded SQL statement. Learning about the rules, guidelines, and types of subqueries used in a SQL statement. The rules and guidelines when using subqueries are the following. A subquery must be enclosed in parentheses. Place the subquery on the right side of the comparison condition for readability. However, the subquery can appear on either side of the comparison operator. Two classes of comparison conditions are used in subqueries: single row operators and multiple row operators. The two types of subqueries that we will learn about are the single row subqueries and multiple row subqueries. Single row subqueries are queries that return only one row from the inner select statement. Multiple row subqueries are queries that return more than one row from the inner select statement. Note, there are also multiple column subqueries. These are queries that return more than one column from the inner select statement. The multiple column subquery will not be covered in this video. You have now learned about the rules and guidelines when using subqueries in your SQL statements, and we have introduced the two types of subqueries. Using a single row subquery to return one row to an outer query in a SQL statement. A single row subquery is one that returns one row from the inner select statement. This type of subquery uses a single row operator. The list of single row operators are equal to, greater than or equal to, less than or equal to, and not equal to. A select statement can be considered as a query block. The example in the slide displays employees who do the same job as Taylor but earn a greater salary than him. The example consists of 3 query blocks, the outer query and 2 inner queries. The inner query blocks are executed first, producing the results SA_rep and 8600 respectively. The outer query block is then processed and uses the values that were returned by the inner queries to complete its search conditions. Both inner queries return single values, SA_rep and 8600 respectively. This SQL statement is therefore called a single row subquery. Note, the outer and inner queries can get data from different tables. To demonstrate a single row subquery, we would like to display the employees whose job ID is the same as that of employee 141. We will start by writing the inner query, and we will then expand our SQL statement to include the outer query. Our SQL statement will look as follows. First, we would like to identify the job ID for employee ID 141. We will select Job ID from Employees, where Employee ID is equal to 141. Let's execute this statement. In the query result, the job ID returned is ST_clerk. We will now include our outer query. We would like to see all other employees who have the job ID ST_clerk. To do this, we're going to select last name, job ID from the employees table, where the job ID is equal to the job ID in our subquery. It is not necessary to align it, but in order to make it easy to read, we will do so. We will close off our subquery with a parentheses. Let's execute our statement now. In the query result, we've returned a list of all employees with the job title ST_clerk. You are now ready to use a single row subquery to return one row to an outer query in your SQL statement. In this video, we will learn how to use a group function in an inner query to return a single row to an outer query. You can display data from a main query by using a group function in a subquery to return a single row. The subquery is in parentheses and is placed after the comparison condition. The example in the slide displays a list of all employees who receive the minimum salary. The inner query selects the minimum salary from the employees table by using the min group function. This single value is then passed to the where clause in the outer query. The outer query selects all employees' last name, job ID, and salaries, where their salary is equal to the minimum salary value. We are in our SQL Developer session and connected to our HR connection. To demonstrate the use of a group function in a subquery, we would like to return all employees who earn less than or equal to the average salary. First, we're going to write the inner query. The SQL statement looks as follows. We're going to select, we will round the average salary to 0 decimal places, and we're selecting from the employees table. Let's execute this statement and review the output. In the query result, we can see the average salary across all employees rounded to 0 decimal places is 6495. Let's now extend our SQL statement to include the outer query. To do this, we will select the employee ID, their last name, and their salary from the employees table, where the salary is less than or equal to the average salary returned in our subquery. We remember to enclose our subquery in parentheses. We will include an order by clause in our outer query. We will order by salary descending. Let's execute this statement now and review its output. In the query result, we've returned the employee ID, last name, and salary for all employees whose salary is less than or equal to the average salary across all employees. You are now ready to start using a group function in your subquery in a SQL statement. In this video, we will learn about the use of a subquery in the having clause of a SQL statement. You can use subqueries not only in the where clause, but also in the having clause. The Oracle server executes the subquery first, and the results are returned into the having clause of the main query. The SQL statement in the slide displays all the departments that have a minimum salary greater than that of Department 30. The subquery selects the minimum salary for Department 30 and then passes the result into the having clause of the main query. To demonstrate the use of a subquery in the having clause of a SQL statement, we're going to write a query to find the job with the lowest average salary. First, we will write the subquery. It is not a requirement for us to do this first, but it is good for us to know the value that will be returned by the subquery. Our subquery will look as follows. We will select the minimum average salary from employees, and we will group by the job ID. Let's execute this statement first. In the query result, we can see the minimum average salary is 2763. Let's now extend our SQL statement to include the main query. We would like to select the job ID and the average salary from the employees table. We will group by the job ID, and we will include the having clause, having an average salary equal to our subquery. Let's execute this statement and review the output. In the query result, we can see that st_clerk is the job with the lowest average salary. And that is how we use a subquery in the having clause of a SQL statement. In this video, we're going to identify common errors that occur when an incorrect number of rows is returned by a single row subquery in a SQL statement. A common error with subqueries occurs when more than one row is returned for a single row subquery. In the SQL statement in the slide, the subquery contains a group by clause, which implies that the subquery will return multiple rows, one for each group that it finds. The outer query takes those results and uses them in its where clause. The where clause contains the equal to operator, a single row comparison operator that expects only one value. The equal to operator cannot accept more than one value from the subquery and therefore generates an error. To correct this error, change the equal to operator to in. Another common problem with subqueries occurs when no rows are returned by the inner query. In the SQL statement in the slide, the subquery contains a where clause. Presumably, the intention is to find the employee whose name is Haas. The statement is correct, but selects no rows when executed. This is because there is no employee named Haas. Therefore, the subquery returns no rows. The outer query takes the results of the subquery and uses these results in its where clause. The outer query finds no employee with a job ID equal to null, and so returns no rows. If a job existed with a value of null, the row is not returned, because the comparison of two null values yields a null, and therefore the where condition is not true. In our SQL Developer session, we have the SQL statement from the first slide. Let's execute this statement. In the query result, we can see an error is returned. Error-01427, single row subquery returns more than one row. If we execute just the subquery, we can see that multiple rows are returned. One row is returned per department ID. Let's change the equal to sign to the in operator and execute our statement. The SQL statement now executes successfully. Looking now at the SQL statement when no rows are returned by the inner query. If we first execute our SQL statement, we will see no rows are returned. If we execute the subquery, no rows are returned. This is because there is no employee with the last name Haas. The result of this is that a null is returned to the where clause. If a job existed with a null value, the row would not be returned, as the comparison of two null values yields a null, and therefore the condition is not true. In this video, we have identified common errors that occur when an incorrect number of rows is returned by a single row subquery in a SQL statement. In this video, we will describe the use of multiple row subqueries in a SQL statement. Subqueries that return more than one row are called multiple row subqueries. You will use a multiple row operator instead of a single row operator with a multiple row subquery. The multiple row operator expects one or more values. These operators are the following. The in operator. In is equal to any member in the list. Any. The any operator must be preceded by an equal to sign, not equal to, greater than or equal to, and greater than or equal to. True is returned if at least one of the elements exists in the result set of the subquery for which the relation is true. All. The all operator must be preceded by equal to, not equal to, greater than or equal to, or greater than or equal to. True is returned if the relation is true for all elements in the result set of the subquery. To demonstrate the use of the in operator in a multiple row subquery, our SQL statement will find the employees who earn the same salary as the minimum salary for each department. The inner query is executed first, producing the query result. The main block is then processed and uses the values that were returned by the inner query to complete its search condition. In our SQL statement, we're going to select the last name, salary, department ID from the employees table, where the salary is in, and in our subquery, we select the minimum salary from the employees table, and we group by the department ID. We then sort the rows returned by last name, salary, and department ID. First, we will execute our subquery to identify the rows that are being returned. In the query result, we can see the minimum salary per department ID is returned. Let's now execute our whole SQL statement and review the output. In our query result, we can see the employee's last name, salary, and department IDs are returned for all employees whose salary is in the list defined in our subquery. Our second SQL statement is how the query appears to the Oracle server. We still select last name, salary, department ID from the employees where the salary is in and a list of values. These are the values that would have been returned by our subquery. If we execute this SQL statement, the results would be the same. In this video, we've covered the use of multiple row subqueries in a SQL statement, and we've worked with the in operator in a multiple row subquery. The any and all operators will be covered in a future video. Using the any and all operators in multiple row subqueries in a SQL statement. The any operator and its synonym, the sum operator, compare a value to each value returned by the subquery. The example in this slide displays employees who are not IT programmers and whose salary is less than that of any IT programmer. The maximum salary that a programmer earns is $9,000. Less than any means less than the maximum, greater than any means more than the minimum, and equal to any is equivalent to in. The all operator compares a value to every value returned by a subquery. The example in the slide displays employees whose salary is less than the salary of all employees with the job ID of IT_prog and whose job is not IT_prog. Greater than all means more than the maximum. Less than all means less than the minimum. The not operator can be used with the in, any, and all operators. We are in our SQL Developer session, and in our first SQL statement, we will write a query containing the any keyword when comparing values with the multiple row subquery. We are selecting where the commission % column is compared to each value returned by the subquery, and where it is more than the minimum value, the row is returned. Our SQL statement looks as follows. We will select the employee ID, the last name, and the commission % column from the employees table, where the commission % is greater than any, and in our subquery we select commission % from the employees table, where the job ID is equal to SA_rep. Let's first execute this subquery to review the rows that are returned. In the query result, the commission % is returned for every employee whose job ID is equal to SA_rep. Let's now complete our SQL statement. As we would like to add in another condition, we will specify where the job ID is not equal to SA_rep. Let's execute our statement. In the query result, we return all employees whose job ID is not equal to SA_rep and where their commission percent is greater than the minimum value returned by the subquery. We're now going to update our SQL statement and change the keyword any to all. The commission percent column will now be compared to every value returned by the subquery, and where every value meets the condition, the row will be returned. Let's execute this statement. In the query result, we've returned the employees whose job ID is not equal to SA_rep and where the commission percent is greater than the maximum commission percent returned by the subquery. You are now ready to start using the any and all operators in multiple row subqueries in your SQL statements. In this video, we will learn how to use a multiple column subquery to return more than one column to the outer query in a SQL statement. A multiple column subquery returns more than one column to the outer query. Column comparisons in a multiple column comparison can be pairwise or non-pairwise and can be listed in the outer queries from, where, or having clauses. Should you want to compare two or more columns, you must write a compound where clause using logical operators. Multiple column subqueries enable you to duplicate where conditions into a single where clause. The in operator is used to check a value within a set of values, and the list of values may come from the results returned by a subquery. The example in the slide contains a multiple column subquery. This is because the subquery returns more than one column. The inner query is executed first, and it returns the lowest salary and department ID for each department. The main query block is then processed and uses the values that were returned by the inner query to complete its search condition. To demonstrate a multiple column subquery, we are logged into our HR connection in SQL Developer. We would like to display the employee with the highest salary in each department. Our SQL statement will look as follows. First, we will write a subquery to identify the maximum salary per department ID. We will select max salary, department ID from the employees table, and we will group by department ID. Let's execute this statement and review its output. In the query result, we can see we've returned the maximum salary value per department ID. Let's extend this SQL statement now, as we would like to see the employee that earns the maximum salary per department. To do this, we'll enclose our subquery in brackets, and we'll then include the outer query block. We will select the employee ID, the department ID, and the salary from the employees table, where salary, department ID is in, and we include our subquery. We would then like to sort our data to be returned by department ID. We will include the order by clause. Let's execute our SQL statement and review the output. In the query result, we show the employee per department with the highest salary. And that is how we write a multiple column subquery in a SQL statement. In this video, we will describe the use of null values and the not-in operator in a subquery in a SQL statement. The SQL statement in the slide attempts to display all the employees who do not have any subordinates. The SQL statement, however, does not return any rows. One of the values returned by the inner query is a null value, and therefore the entire query returns no rows. The reason for this is that all conditions that compare a null value result in a null. Whenever null values are likely to be part of the result set of a subquery, do not use the not-in operator. The not-in operator is equivalent to not equal all. Notice That the null value as part of the result set of a subquery is not a problem if you use the in operator. This is because the in operator is equivalent to equal any. We are logged into our HR connection in SQL Developer. To demonstrate the effect of null values when using the not in operator, we have the SQL statement from our slide. Let's execute this statement. We can see that no rows are returned. This is because if we execute our subquery alone, we can see that there are null values returned. When evaluating a null value and using the not in operator, no rows will be returned. Let's modify this SQL statement to ensure it returns rows. To do this, we will include a where clause in our subquery. We will return only rows from the employees table where the manager ID is not null. Let's execute this statement now. We can see now in our query result that rows have been returned. We've returned a list of all employees that do not have subordinates. We would now like to view a list of the employees who do have subordinates. Taking the same SQL statement from our slide, we will amend our SQL statement to use the in operator. If we then execute our SQL statement, as the in operator evaluates to equal any, the fact that there are null values returned in our subquery is not an issue. In the query result, we've returned a list of the employees who have subordinates reporting to them. As you can see, null values will result in your SQL statement not returning the expected rows when you make use of the not in operator. Now that you've learned how to use subqueries in your SQL statement, it is time to put that knowledge to work. In this exercise, you will write a series of SQL statements to return data for the following reports. Create a report that displays the employee number, last name, and salary of all employees who earn more than the average salary. Sort the results in ascending order by salary. Next, write a query that displays the employee number and last name of all employees who work in a department with any employee whose last name contains the letter U. Lastly, create a report that displays the last name for all employees whose salary is more than the salary of any employee from Department 60. When you are ready, pause this video and perform the exercise. When you are done, come back to the video and I will work through the exercise with you. To demonstrate the solution to the exercise, we are connected to our HR connection in SQL Developer. For our first task, we will write a SQL statement that returns the employee number, last name, and salary for all employees who earn more than the average salary, and we will sort the results by salary ascending order. First, we need to calculate the average salary from the employees table. To do this, we will select, using the average function, we will calculate the average salary from employees. Let's execute this statement. And in the query result, we return the average salary. This SQL statement will make up our subquery. We're now going to write the outer query. We would like to select the employee ID, their last name, and salary from the employees table where the salary is greater than the average salary as returned by our subquery. We would like to select all employees who have a salary greater than the average salary. We would also like to sort our data by salary. We will order by salary ascending. Let's execute this statement. In our query result, we've returned a list of employees who earn a salary greater than the average salary, and our data is returned ordered by salary ascending order. For this next task, we need to write a SQL statement that displays the employee number and last name for all employees who work in a department with any employee whose last name contains the letter U. First, we'll write a subquery to identify the department ID For employees whose last name contains a letter U, the SQL statement will look as follows. We will select Department ID from the Employees table where last name like a U. Let's execute this statement. In the query result, we've listed all the department IDs where an employee's last name contains a letter U. This SQL statement will make up our subquery. To write the outer query, we would like to select the employee ID and last name from the employees table where the department ID is in. We compare it to the department ID from our subquery. Let's execute this statement. In our query result, we've returned a list of all employees who work in the same department as any employee whose last name contains a letter U. For the last task in this exercise, we will write a SQL statement that will display a list of all employees whose salary is more than the salary of any employee in Department 60. First, we start with our subquery. We select Salary from the Employees table where the Department ID is equal to 60. We would like to see the salary for all employees in Department 60. Now we're going to extend our SQL statement as we would like to see all employees who have a salary greater than any of these salaries. Let's write our outer statement. We will select the last name from the employees table where the salary is greater than any of the values returned in our subquery. Let's execute our SQL statement. In the query result, we display a list of all employees whose salary is greater than the salary of any employee in Department 60. DML, or Data Manipulation Language, as it is known, is a core part of SQL. When you want to add, update, or delete data in the database, you execute a DML statement. To add a new row into a table, we use the insert statement. To modify an existing row in a table, we use the update statement. And to remove existing rows, we use the delete or truncate statement. A collection of DML statements that form a logical unit of work is called a transaction. We will discuss in more detail database transaction control using commit, rollback, and save point in future videos. Let's now consider a banking database. When a bank customer transfers money from a savings account to a checking account, the transaction might consist of 3 separate operations: decreasing the savings account, increasing the checking account, and recording the transaction in the transaction journal. The Oracle server must guarantee that all 3 SQL statements are performed to maintain the accounts in proper balance. When something prevents one of the statements in the transaction from executing, the other statements of the transaction must also be undone, thereby ensuring a consistent view of the data at all times. Note, most of the DML statements in this course assume that no constraints on the table are violated. Constraints will be discussed in a later video. In SQL Developer, click the Run Script icon or press F5 to run the DML statements, and the feedback messages will be shown on the Script Output tab. In this video, we have introduced you to DML, or Data Manipulation Language as it is known. DML is a core part of SQL. Adding new rows to a table in the database. The Public Relations Department is new and needs to be added to the Departments table in the database. To do this, a new row will be inserted into the departments table. New rows are added to a table by issuing the insert statement. The syntax for the insert statement is insert into. We then specify the table name, and in brackets the columns in which the data will be inserted into. The values clause is specified, and in brackets the data that will be inserted into each of the specified columns. It is good practice to prefix the table name with the schema or owner name. For example, our tables are all owned by HR, and we would then specify the table name. For example, HR.departments. This insert statement, which includes the values clause, adds only one row at a time to a table. As we can insert a new row that contains values for each column, the column list is not required in the insert clause. However, if you do not use the column list, the values must be listed according to the default order of the columns in the table, and a value must be provided for each column. For clarity, it is good to use the column list in the insert clause. Character and date values must be enclosed within single quotation marks. However, it is not recommended that you enclose numeric values within single quotation marks. To insert a new row into our departments table, we are logged into our HR connection in SQL Developer. We would like to add a new department called Distribution to our departments table. We're only going to insert values into some of the columns in the departments table. Let's first describe the departments table so that we can see which columns exist. In our departments table, we have a department ID column, a department name, a manager ID, and location ID. Let's now insert a row into this table. We will insert into the departments table. We're going to insert into the department ID column, the department name column, and the location ID column. We include the values keyword, and we specify our data in brackets. We'll give it a department ID of 280. The department name is Distribution, and it will be in location 1700. Let's execute this insert statement. We can see that one row is inserted into our table. We will then issue the commit statement. This is so that the change is made permanent in the database. We will cover the commit statement in a future video. Including the column names is not mandatory if data is inserted into all columns, but it is recommended for clarity. The same with the schema name. It is not mandatory but recommended, as you may encounter problems where a table with the same name could exist in other schemas in the database. We will now demonstrate an example where we do not specify the column name. We insert into HR.departments. We then specify the values keyword, and we list the data that we wish to insert. We execute this statement. One row is inserted into our departments table. We issue the commit statement. Let's now query our departments table to view the rows that have been added. In our query result, we can see that Department 280, our distribution department, and Department 290, our new internal sales department, have been added to the departments table. Now you know how to add new rows to a table in the database. In this video, we will learn how to insert rows with null values into a table. Before we can use null values, we need to ensure that the columns where null values will be inserted allow for null values. This we can do with the describe command. The Oracle server automatically enforces all data types, data ranges, and data integrity constraints. Any column that is not listed explicitly obtains a null value in the new row, unless you have default values for the missing columns that are used. There are two methods for inserting null values. The first method is the implicit method. The implicit method is used by simply omitting the column name from the column list in the insert statement. The explicit method. The explicit method is used when we specify the null keyword in the values list. For character strings and dates, we specify an empty string. Common errors that can occur during user input are checked in the following order. Mandatory value missing for a not null column. Duplicate value violating any unique or primary key constraint. Any value violating a check constraint. Referential integrity maintained for foreign key constraint. Data type mismatches or values too wide to fit in a column. The use of the column list is recommended because it makes the insert statement more readable and reliable, and less prone to mistakes. We will now insert rows into the departments table to demonstrate the implicit and explicit methods for inserting rows with null values. First, we will describe the departments table to ensure that null values are allowed. To do this, we describe hr.departments. In the script output, we can see that the Manager ID and Location ID columns allow for null values. Demonstrating now the implicit method, we will insert into the Departments table. We're going to insert values for the Department ID column and the Department Name column. We then specify the values keyword and we insert the data. We will give it Department ID 300 and we will give the department name Demonstration. Let's execute this insert statement. In the script output, we can see that one row has been inserted into the departments table. Next, we will demonstrate the explicit method, and our insert statement will look as follows. Insert into HR departments. And we do not specify any columns. We will specify the keyword values and the data that we're going to insert. We'll give it Department ID 310. The department name will be called Motoring. And we will explicitly define null values for the Manager ID and for the Location ID columns. Let's execute this insert statement. We can see another row has been inserted. Let's issue the commit statement for these changes to be made permanently to the departments table. Selecting now from the departments table, we're going to select all rows from the departments table and we're going to order by department ID descending. We would like to see if our new rows have been inserted and review the null values. In the query result, we can see where we specified the implicit method. For Department ID 300, the Manager ID and Location ID are null. For Department ID 310, where we defined the explicit method, we can see the Manager ID is null and the Location ID is null. And that is how we use the implicit and explicit methods to insert rows with null values into our tables. In this video, we're going to look at the use of functions to insert special values when adding rows to a table. Functions such as sysdate, current date, and user can be included in the insert statement. There are many more Oracle functions that can also be used. The example in the slide records information for employee pop in the employees table. It supplies the current date and time in the higher date column. The current date function is used to return the current date in the session time zone. You can also use the user function when inserting rows in a table. The user function records the current username. To demonstrate the insert of special values when working with the insert statement, in our SQL statement, we are going to create a new user in the employees table. We're going to make use of the user function. We're going to insert the current session's username into the first name field in the employees table. Let's execute the SQL statement. We can see in the script output, one row is inserted into the employees table. Let's issue our commit statement to write this record to the database. Let's issue the commit statement to save this record permanently to the employees table. Let's now select from the employees table to view the output. Let's select from our employees table to view the row that we have just inserted. As we specified the user function for the first name, we can see that the first name is now set to HR. Our current session is connected with the HR user. And that is how we insert rows with special values into a table. Working with specific date and time values when adding rows to a table using the insert statement. The dd-mon-rr format is generally used to insert a date value. With the RR format, the system provides the correct century automatically. You may also supply the date value in the dd-mon-YYYY format. This is recommended because it clearly specifies the century and does not depend on the internal RR format logic of specifying the correct century. If a date must be entered in a format other than the default format, for example, with another century or a specific time, you must use the toDate function. The example in the slide records information for employee Rafili in the employees table, where it sets the higher date column to the 3rd of February 2003. We are logged into our HR connection in SQL Developer. To demonstrate inserting a specific date and time value, we have two insert statements. In the first insert statement, we use the date format dd-mon-YYYY to insert the date into the higher date column. Let's insert this row into our employees table. In the script output, we can see that one row is inserted. For our next insert statement, where we add a new employee to the employees table, we make use of the toDate function to change the date format. Let's execute this insert statement. In the script output, we can see that a second row has been inserted. Let's select from the employees table to view these rows. In the query result, we can see the 2 rows that we inserted into the employees table. And in the higher date column, the date is displayed with the default date format. You are now ready to insert new rows into your tables and specify specific date and time values. In this video, we will learn how to save commands with substitution variables to a file and execute the commands in the file. We will use the ampersand substitution in a SQL statement to prompt for values. The ampersand is a placeholder for the variable value. The example in the slide records information for a department in the departments table. When you run the script file, you will be prompted for input for each of the ampersand substitution variables. After entering a value for the substitution variable, click on the OK button. The values that you input are then substituted into the statement. This enables you to run the same script file over and over, but supply a different set of values each time you run it. To demonstrate using a script and variables to insert rows into a table, we are logged into our HR connection in SQL Developer. We are going to use a script to insert new rows into the departments table. Our insert script will look as follows. We will insert into departments. We'll specify the columns, the department ID and the department name. We include the values keyword, and we will prompt for the department ID and the department name. As department name is a character data type, we need to enclose it in single quotes. I will include the commit statement in my script. Let's save our script. We will call our script insert variable. We save the script. Our script has now been saved. I'm going to open a new SQL worksheet window, and we will execute our script from this new worksheet window. At the SQL worksheet window, as I've saved my script in the default location for my SQL Developer environment, all I need to do is enter the @ sign and the name of my script. Let's execute the script now. When we execute the script, we are prompted for the substitution variables. The first substitution variable is the department ID. We will create department ID 320. We are then prompted for the department name. Our department name will be IT Hardware. We click on the OK button, and we can see in the script output that we have one row inserted into our departments table. Let's now select from our departments table to view our new row that has been inserted. Let's execute our select statement. In the query result, we can see that we now have department ID 320 with the department name IT Hardware. Our manager ID and location ID columns are null, as we did not specify them as part of our insert statement. You now know how to save commands with substitution variables to a file and then execute the commands in the file. Using the insert statement to copy rows from one table to another. You can use the insert statement to add rows to a table where the values are derived from an existing table. In the example in the slide, for the insert into statement to work, you must already have created the sales reps table using the create table statement. The create table statement will be discussed in a future video. In place of the values clause, we will use a subquery. The syntax is insert into the table name. You can then specify the columns in brackets, followed by the subquery. The number of columns and their data types in the column list of the insert clause must match the number of values and their data types in the subquery. All rows returned by the subquery are inserted into the sales reps table. 0 or more rows are added depending on the number of rows returned by the subquery. Let's go to our SQL Developer session and use the Insert Into clause to insert new rows into a table by making use of a subquery. We have created a new table called sales_reps, and we would now like to insert information regarding the sales reps from the employees table into our new table. Let's first describe the sales reps table. In the script output, we can see that our sales reps table consists of 4 columns: ID, name, salary, and commission percent. Let's select from this table to see if there are any rows in the table. Currently, there are no rows in this table. We are now going to use our insert SQL statement from the slide to populate the sales reps table. The SQL statement will look as follows. Insert into the sales reps table. We will specify the columns that we're going to insert into. And we will then include our subquery. To populate those columns, we're going to select the employee ID, the last name, the salary column, and the commission percent column from the employees table. And we're going to include a where clause. We would only like to insert rows where the job ID contains the letters rep. Let's execute this insert statement. In the script output, we can see that there are 35 rows inserted into our sales reps table. Let's re-execute our select statement. In the query result, we can now see in the query result that there are 35 rows in our sales reps table. To ensure that these rows are written permanently to the sales reps table, we need to issue the commit statement. We would now like to copy all rows from the employees table into a temporary table we have called copy_emp. To do this, let's first describe our copy_emp table. In the script output, you can see the columns and their data types. This table is an exact copy of the employees table. Let's now insert into this table. We're going to insert into hr.copy_emp. We are not going to specify column names. And in our subquery, we're going to select all columns from the employees table. We do not include a where clause, so all rows from the employees table will be inserted into the copy_emp. Let's execute this statement. In the script output, we can see 110 rows have been inserted. Let's select from our copy_emp table. And we can see that the data has been populated. To make this change permanent, we would need to issue a commit statement. We can see that all the rows from the employees table have been inserted into the copy_emp table. Now you know how to use a subquery to copy rows from one table to another. In this video, we will learn how to change data in a table using the update SQL statement. We make use of the update SQL statement when we need to modify existing data values in a table. For example, in this slide, we need to change the rows for employees in Department 60 and update the department number for these employees to Department 80. The syntax for the update statement is update followed by the table name. Then we specify the set keyword followed by the column in the table to be populated. Equal to value, where value is the corresponding value or subquery for the column. We can then include a condition. The where condition identifies the rows to be updated and is composed of column names, expressions, constants, subqueries, and comparison operators. More than one row can be updated at a time if required. We confirm the update operation by querying the table to display the updated rows. For additional information, see the section on Update in the Oracle Database SQL Language Reference for 12c database. In general, use the primary key column in the where clause to identify a single row for update. Using other columns can unexpectedly cause several rows to be updated. For example, identifying a single row in the employees table by name may return more than one employee having the same name. The update statement modifies the values of a specific row or rows if the where clause is specified. The first example in this slide shows the transfer of employee 113 to Department 50. Should you omit the where clause, the values for all the rows in the table are modified. In the second example, all rows in the copy_emp table will be updated, and the department ID will be set to 110 for all employees as the where clause has been omitted. To update a column to a null value, we specify the null keyword. We set column name equal to null. Let's go to our SQL Developer session and demonstrate the update SQL statement. To demonstrate the update SQL statement, we would like to update the department ID for all employees in Department 60 and set the department ID equal to Department 80. First, let's write a select statement to view the last name and department ID for all employees in Department 60. We will select last name, department ID from the employees table where department ID is equal to 60. In the query result, we can see we have 7 employees currently in Department 60. Let's now write our update statement to set their department IDs to 80. The syntax is as follows. Update, and we specify the table name. Set department ID equal to 80, where department ID is equal to 60. So all employees whose department ID is equal to 60, their rows will now be updated and their department IDs will be set to 80. Let's execute this update statement. In the script output, we can see that 7 rows have been updated. Let's run our SQL statement again. In our query result, we can see that now in the employees table, we do not have any employees in Department 60. For this change to be made permanently to the table and to be viewed by other sessions, we would need to issue the commit statement. Should we not include a where clause, all rows will be updated. To demonstrate this, we will set the department ID equal to 110 and we will omit the where clause in our copy_m table. The copy_m table contains the same data as the employees table. First, we're going to select from the copy_m table to verify the departments. We will select the employee's last name and their department ID from the copy_m table. In the query result, we can see that the employees have different department IDs. Let's now write our update statement. We will update the copy_m table and we will set the department ID equal to 110. We've not included a where clause in this update statement. In the script output, we can see that 110 rows have been updated. Let's now run our select statement again and view the output. In our query result, we can see that all employees now have the same department ID. This is because we omitted the where clause in our update statement. In this video, you have learned how to change data in a table using the update SQL statement. Changing data in two columns using a subquery to update the two columns in the update SQL statement. You can update multiple columns in the set clause of an update statement by writing multiple subqueries. The example in this slide updates the job ID and salary values for employee ID 103 to be the same as the job ID and salary values for employee 205. Looking at the syntax to update multiple columns, we can specify multiple columns in the set statement. The example in the slide shows two columns being updated based on the values from one subquery. We can also update multiple columns by specifying the first column equal to a value from the subquery, comma, and then specify the next column equal to a value from its own subquery. To demonstrate how to update two columns with a subquery, employee with the ID 180, employee Taylor, has moved from being an ST_clerk to a purchasing clerk. We need to update the employee information to reflect the new job ID and Taylor's new manager. We will update the manager ID and the job ID for Taylor to be the same as employee 115, Alexander Chu. Alexander Chu is a purchasing clerk reporting to manager 114. Let's first view the existing data in the table for these two employees. We will select the employee ID, their last name, their manager ID, and their job ID from the employees table where employee ID is in, and we will select employee ID 115 and employee 180. Let's execute this statement. In the query result, we can see employee Chu has the manager ID 114 and is a purchasing clerk, and employee Taylor currently has manager ID 120 and has the job ID ST_clerk. We are now going to update employee Taylor. Our update statement will look as follows. We will update the employees table, we will set the manager ID and the job ID equal to, we will now specify our subquery. We will select the manager ID and the job ID from the employees table. As we would like to set it to the same as employee 2, we will specify where employee ID is equal to 115. We will then include a where clause, as we would only like to update this value for employee Taylor. We will therefore include where employee ID is equal to 180. Let's execute this statement. In the script output, we can see that one row has been updated. Let's select from our table again to view the values for the 2 employees. In the query result, we can now see that both employees have the same manager ID and job ID. I have taken the same update statement and written it to update each column separately. This would be if we needed to update the manager ID from one subquery and then update the job ID based on a different subquery. We could write the SQL statement as follows. It would be update your table, set the first column, the manager ID, equal to, and we then specify our first subquery. We select the manager ID from the employees table where the employee ID equals to 115. We then include a comma and we specify our next column equal to the second subquery. As we were only updating one row, we included our where clause where employee ID equals to 180. The result of this SQL statement would be the same as our previous update statement. In this video, we've covered changing data in 2 columns using a subquery to update the 2 columns in the update SQL statement. In this video, you will learn how to change the rows in a table based on a different table using the update SQL statement. You can use subqueries in the update statement to update values in a table. In the example in this slide, we update the copy_m table based on the values from the employees table. The department ID column in the copy_m table is updated to be set to the same value as employee ID 100 in the employees table, based on a subquery. We have a subquery included in the where clause, as we would like to update the department ID in the copy_m table where the job ID in the copy_m table is equal to the job ID in the employees table, and where the employee ID is equal to 200 in the employees table. To demonstrate how to change the rows in a table based on a different table using the update SQL statement, we have a SQL statement that will update the location ID in the departments table where the employee's job ID is equal to AD_Perez. We have created a copy of the departments table for the purpose of this exercise. First, we will select from our table to view the current department ID. Our SQL statement will look as follows. We will select all rows from our copy department table where the department ID is in, and we select the department ID from the employees table where the job ID is equal to AD_Perez. With this SQL statement, we're just going to view the rows currently in the table. In the query result, we can see that the department ID is 90 and the location ID is 1700. Our update statement is going to look as follows. We will update our copy underscore dep table. We will set the location ID equal to, and in our subquery, we will select the location ID from the locations table where the state province is equal to California. And we'd like to include a where clause in our update statement, as we would only like to update this table where the job ID is AD_pres. To do this, we'll include where the department ID is equal to, and in our subquery, we will select the department ID from the employees table where the job ID is equal to AD_pres. Let's execute our update statement. In the script output, we can see that one row has been updated. Let's run our select statement again to ensure that the location ID has been updated. In the query result, we can now see for department ID 90, our location ID is now set to 1500. You are now ready to change rows in a table based on a different table using the update SQL statement. Removing rows from a table using the delete SQL statement. This slide shows a graphic where the contracting department has been removed from the departments table. This is assuming that no constraints on the departments table are violated. We can remove existing rows from a table by using the delete statement. The syntax for the delete statement is delete from, and we then specify the name of the table. The condition identifies the rows to be deleted and is composed of column names, expressions, constants, subqueries, and comparison operators. Note, if no rows are deleted, the message 0 rows deleted is returned. For additional information, see the section on delete in the Oracle Database SQL language reference for 12c database. Specific rows can be deleted by specifying the where clause in the delete statement. In the first example in the slide, the statement deletes the accounting department from the departments table. You can confirm the delete operation by displaying the deleted rows using the select statement. Select star from departments where department name equals finance. If you, however, omit the where clause, all the rows in the table are deleted. The second example in this slide deletes all rows from the copy_emp table. This is because no where clause was specified. To demonstrate using the delete statement to remove rows from a table, in our first SQL statement, we would like to delete employee Don Jones from a copy of the employees table. We created a table called copy_emp_del for the purpose of this exercise. First, let's select from our table. We will select star from copy_emp_del. We can see in the query result, the rows are an exact match of the rows that are in our employees table. Let's now extend this SQL statement to identify the employee Don Jones. We will include a where clause where his first name is equal to Don and his last name is equal to Jones. We would like to identify his employee ID number. In our query result, we can see we have two entries for employee Don Jones. We need to clean up the second entry, so we will be deleting employee ID 230. To delete this row, our statement will look as follows. Delete from our copy table, hr.copy_emp_del, where the employee ID is equal to 230. Let's execute this statement. In our script output, we can see that we have deleted one row from this table. Let's execute our select statement again. In the query result, we can see that we now only have one entry for employee Don Jones. To demonstrate an example where we can delete more than one row, we would like to delete two departments. I've created a copy of the departments table called copy_dep_del for the purpose of this exercise. Our delete statement will look as follows. Let's first select from our copy table. We will select star from the hr.copy_dep_del table. In our query result, we can see we have a list of all the departments. In this video, you will learn how to remove rows from a table based on a different table using the delete SQL statement. You can use subqueries to delete rows from a table based on values from another table. The example in this slide deletes all the employees in a department where the department name contains the string public. The subquery searches the departments table to find the department number based on the department name containing the string public. The subquery then feeds the department number to the main query, which deletes rows of data from the employees table based on this department number. We are connected to our HR connection in SQL Developer. We would like to delete the departments from the departments table where there are no employees in that department and where the department ID is equal to 300 or greater. Our delete statement will look as follows. Delete from the departments table where the department ID is not in, and we will write our subquery. We will select the department ID from the employees table where the department ID is not null. In our subquery, we are selecting a list of the department IDs in the employees table where the department ID is not null. We will then include an additional condition in our delete statement. We would only like to delete where our department IDs are equal to or greater than 300. Let's execute this statement. In our script output, we can see that we have deleted 3 rows from the departments table. To delete these rows permanently from the table, we would need to issue the commit statement. We will cover the commit statement in a future video. And that is how we remove rows from a table based on a different table using the delete SQL statement. Using the truncate SQL statement to delete all rows from a table. A more efficient method of emptying a table is by using the truncate statement. You can use the truncate statement to quickly remove all rows from a table or cluster. All rows are removed, leaving the table empty with the table structure intact. Removing rows with the truncate statement is faster than removing them with the delete statement. This is because the truncate statement is a data definition language or DDL statement, and it generates no rollback information. Rollback will be covered in a future video. It is not an easy task to recover from a truncate statement. The syntax for the truncate statement is truncate table followed by the table name. If the table is the parent of a referential integrity constraint, you cannot truncate the table. You would need to disable the constraint before issuing the truncate statement. We will cover the disabling of constraints in a future video. To demonstrate the truncate statement, we have created a copy of the departments table called copy_dept. We will remove all the rows from the copy_dept table using the truncate statement. Let's first view the data in our copy_dept table. We will select star from hr.copy_dept. We can see in the query result we have 32 rows in our copy_dept table. Let's now issue our truncate statement. The syntax is truncate table, and we then specify the table name, copy_dept. Let's execute our truncate statement. In the script output, we can see that the table has been truncated. Let's now select from our table again. We can now see in the query result that there are no rows in our copy_dept table. Remember, when using the truncate statement, it is not an easy task to recover the data if the rows were deleted in error. In this video, you have learned how to delete all the rows from a table using the truncate SQL statement. Now that you've learned the basics of working with data manipulation in a table, it is time to put that knowledge to work. In this exercise, you will create an insert statement to add the first row of data to the my_employee table from the sample data below, without listing the columns in the insert clause. Next, you will write an insert statement in a dynamic reusable script file to load the rest of the rows into the my_employee table, prompting for all the columns. Save the script to a file and execute this script to populate the table with the remaining rows. Lastly, you will change the salary to $1,000 for all employees with a salary of less than $900 and make the changes permanent. For this exercise, you will first need to create the my_employee table from the provided create script. When you are ready, pause this video and perform the exercise. When you are done, come back to the video and I will work through the exercise with you. We are logged into our HR connection in SQL Developer. Before starting with the tasks in this exercise, we need to create the my_employee table. Make use of the provided script to create this table. Let's create our table. In the script output, we can see we have created the my_employee table. For the first task in the exercise, we needed to create an insert statement to add the first row of data, as displayed in the slide, to the my_employee table. We need to insert the row without listing the columns in the insert statement. The insert statement looks as follows. Insert into my_employee We then specify the values keyword and the information from the slide for the first row. Let's execute this insert statement. Let's now select from the table to view the data. We can see in our my_employee table, we have one row inserted into our table. For the next task, we needed to write an insert statement in a dynamic reusable script file to load the rest of the rows into the my_employee table, prompting for all the columns. We need to save the script to a file and execute the script to populate the table with the remaining rows. Our insert statement will look as follows. We will insert into the my_employee table. We specify the values keyword. And for each column, we've included a substitution variable. When we execute this statement, we will be prompted to enter a value for each column. Let's save our script. We will call our script my_employee_insert, and it is a type.sql. Let's click on the Save button, and our script has been saved. I have opened a new SQL worksheet window, and to execute my script, I've entered the @ and the name of the script. As my script is saved in the default scripts location, as configured in my preferences. Let's execute this script. We are prompted for the values to be entered into each of the columns. We will now enter the values to insert the data from the table in the slide. For the ID column, we will enter number 2. For the last name, we will include Danks. The first name is Betty, and the user ID will be bdanks, and her salary is 860. In the script output, we can see that one row has been inserted. Follow this process and insert all the rows from the table in the slide into the my_employee table. Once you have inserted all the rows into the table, let's select from the table to view the data that has been inserted. In the query result, we can see the rows that have been inserted into the my_employee table. For this final task in the exercise, we need to change the salary to $1,000 for all employees with a salary less than $900. And we need to make the changes permanent. Our update statement will look as follows. Update the table name, set the salary column equal to 1,000 where the salary is less than $900. Let's execute the update statement. In our script output, we can see 3 rows have been updated. To make these changes permanent in our database, we will issue the commit statement. Let's issue our commit statement. In the script output, we can see the commit is complete. Let's now select from our table. In the query result, we can see that all employees whose salary was less than $900 have now been updated to $1,000. And these changes have been saved permanently in the database. In this video, we will describe database transactions and how to use database transactions to ensure data consistency during DML, DDL, and DCL activity on the database. The Oracle server ensures data consistency based on transactions. Transactions give you more flexibility and control when changing data, and they ensure data consistency in the event of user process failure or system failure. Transactions consist of DML statements that constitute one consistent change to the data. For example, a transfer of funds between two accounts should include the debit in one account and the credit to another account of the same amount. Both actions should either fail or succeed together. The credit should not be committed without the debit. The types of database transactions consist of three elements. The first, data manipulation language, or DML as it is known. DML is used for managing data within schema objects, such as insert, update, and delete. A DML transaction consists of any number of DML statements that the Oracle server treats as a single entity or a logical unit of work. Next is DDL, the data definition language. DDL is used to define the database structure, for example, to create objects in the database, to alter or drop these objects. A DDL transaction consists of only one DDL statement. The third element, data control language, also known as DCL. DCL is used to manage a user's privileges in the database. A DCL transaction consists of only one DCL statement. In this video, we have described the database transactions and how to use database transactions to ensure data consistency during DML, DDL, and DCL activity on the database. In this video, we will learn about the begin and end of a transaction, and we will describe the commit and rollback SQL statements. When does a database transaction start and end? A transaction begins when the first DML statement is encountered. A transaction ends when one of the following events occurs. A commit or rollback statement is issued. A DDL statement, such as create, is issued. A DCL statement is issued. The user exits SQL Developer or SQL Plus on a machine failure or if the system crashes. After one transaction ends, the next executable SQL statement automatically starts the next transaction. A DDL statement or a DCL statement is automatically committed and therefore implicitly ends a transaction. With the commit and rollback statements, you have control over whether to make changes to the data permanent or not. With the commit and rollback statements, you can ensure data consistency. You can preview data changes before making the changes permanent. And we can group logically related operations. The commit statement will end the current transaction and will make the data change permanent in the database. The rollback statement will end the current transaction by discarding the pending changes. We are in SQL Developer and connected to our HR connection. We will demonstrate the begin and end of a transaction and the use of the commit and rollback statements in a transaction. For our first transaction, we're going to insert a new row into the departments table, and we will issue the commit statement for the data change to be saved in the database and to end our transaction. Our insert statement will look as follows. Insert into departments, the values keyword, and we will create department ID 350. We will give it the name mining. And we will pass null values for the last two columns. Let's execute this insert statement. In the script output, we can see that one row has been inserted. Let's select from the departments table to view this row. We can see that department ID 350 has been inserted into our departments table. To make this change permanent and to end the transaction, we will issue the commit statement. Next, starting a new transaction, we would like to update a row in the departments table, and we will then issue a rollback statement to undo the change and to end the transaction. Our update statement will look as follows. We will update the departments table. We will set the department name equal to test123, where the department ID is equal to 350. Let's execute our update statement. In the script output, we can see that we have updated one row. This change is only valid in our session. Let's select from our departments table to view the change. We can see the department name has been updated. We then realize that this name was updated in error. We would like to discard this change. To do this, we will issue a rollback statement. The rollback statement marks the end of the transaction. Let's select from our departments table to view the row. We can see in the query result that the change has been discarded. In this video, we have learned what makes up the begin and end of a transaction, and we have described the commit and rollback SQL statements. Describing the control of the logic within transactions. You can control the logic of transactions by using the commit, save point, and rollback statements. The commit statement ends the current transaction by making all pending data changes permanent. Save point. The save point marks a save point within the current transaction. Rollback. Rollback ends the current transaction by discarding all pending data changes. The rollback to save point rolls back the current transaction to the specified save point, thereby discarding any changes and/or save points that were created after the save point to which you are rolling back. If you omit the to save point clause, the rollback statement rolls back the entire transaction. Because save points are logical, there is no way to list the save points that you have created. Note, you cannot commit to a save point, as save point is not an ANSI standard. Looking now at the example of a transaction in the slide, at the start of the transaction, we issue a delete statement. We then create save point A, which will allow us to roll back to this save point if needed. After the save point, we issue an insert and an update statement, and we then create save point B. Lastly, we have another insert statement. We are able to undo changes at any point by rolling back to the created save points or by rolling back the entire transaction. Should we not want to roll back, we issue the commit statement to make the data changes for this transaction permanent in the database. And that is how we control the logic within transactions within the database. Using the rollback SQL command to undo changes to a defined marker. You can create a marker in the current transaction by using the save point statement, which will divide the transaction into smaller sections. You can then discard pending changes back to that marker by using the rollback to save point statement. Note, if you create a second save point with the same name as the earlier save point, the earlier save point is deleted. Let's demonstrate the use of the save point and rollback statements by creating a transaction, and we will issue several DML statements. Before starting our transaction, we are first going to view Department ID 350 in the Departments table. We will select all rows from the Departments table where the Department ID is equal to 350. Let's execute this statement. In the query result, if we look at the row for Department ID 350, the department name is Mining and the remaining columns are null. We would now like to update this row and change the department name. Our update statement will look as follows. This update statement will be the start of our transaction. Let's issue the update statement. In the script output, we can see that one row has been updated. Let's select from our departments table to view the row. We can now see that the department name in this session has been updated to test123. At this point, we're going to create a save point. To do that, we specify save point and we give it a name. Let's create our save point. And in the script output, we can see that our save point command has completed. Next, in our transaction, we're going to insert a new department into the departments table. Our statement will look as follows. Insert into the departments table. The values we will insert will be Department ID 360. We will call this the filing department. And the remaining columns we will pass null values. Let's execute our insert statement. In the script output, we can see that one row is inserted. Let's take our select statement and make a copy of it. Update our department ID to 360. And let's view our new row in our departments table. In the query result, we can see that we now have a department ID 360 with the department name Filing. We realize now that Department 360 was created in error. We would like to now roll back to before the insert was done. To do this, we issue the command roll back to save point, and we give it the save point name that we would like to roll back to. Let's roll back the insert statement. And in the script output, we can see that the rollback is complete. Let's update our select statement. We would like to see the records for both Department 350 and 360. Let's execute the SQL statement. In the query result, we can now see that for Department 350, our update statement is still valid, as we rolled back to the point in time after the update statement. Our insert statement, however, has been discarded. This transaction has not ended yet. To end this transaction, we need to either commit or roll back the transaction. We are going to issue the rollback statement to roll back all changes, including the update. In the script output, we can see that the rollback is complete. Let's do one last select from our departments table to view the rows. In the query result, we can now see that the department name is set back to the old department name mining. In this video, we have covered the use of a save point marker and the rollback statement to undo changes to the defined marker in a transaction. In this video, we will describe the conditions in which an automatic commit statement is issued and the impact on the database. An automatic commit takes place when a DDL statement is issued, a DCL statement is issued, and when you exit a SQL Plus or SQL Developer session without explicitly issuing a commit or rollback statement. An automatic rollback takes place during abnormal termination of a SQL Developer or SQL Plus session or during a system failure. In SQL Plus, the auto-commit command can be toggled on or off. If it is set to on, each individual DML statement is committed as soon as it is executed. You then cannot roll back the changes. Let's set our auto-commit to on. We will insert a row into the departments table to test the auto-commit. Insert into the departments table. We'll insert the values 380. Insert test. We will pass null values for the last two columns, and let's enter to execute this insert statement. We can see that one row is created and the commit is complete. This insert cannot be rolled back. Let's set auto commit off. The default is auto commit off. Let's now insert into the departments table. Insert into HR departments, the values 390. We'll insert test 2. In the output, we can see one row is created. We now have the option to explicitly either commit or roll back this statement. The commit statement is automatically issued when you enter a DDL statement or when you exit SQL Plus. In SQL Plus, a normal exit is accomplished by entering the exit command at the prompt. Closing the SQL Plus window is interpreted as an abnormal exit. In SQL Developer, we can set the auto commit on or off. DML is committed on normal exit from SQL Developer only if you have the auto commit preference enabled. To enable auto commit, we click on Tools, we select Preferences, and under Database Advanced, we select the auto commit checkbox. We click on the OK button for the change to take effect. Closing the SQL Developer window is interpreted as an abnormal exit. System failures. When a transaction is interrupted by a system failure, the entire transaction is automatically rolled back. This prevents the error from causing unwanted changes to the data and returns the tables to the state at the time of the last commit. In this way, the Oracle server protects the integrity of the tables. You now know the conditions in which an automatic commit statement is issued and the impact on the database. Describing the state of the database before and after issuing a commit SQL command within the database. Every data change made during the transaction is temporary until the transaction is committed. The state of the data before the commit statement can be described as follows. Data manipulation operations primarily affect the database buffer. Therefore, the previous state of the data can be recovered. The current session can review the results of the data manipulation operations by querying the table. Other sessions cannot view the results of the data manipulation operations made by the current session. The Oracle server institutes read consistency to ensure that each session sees data as it existed at the last commit. The affected rows are locked. Other sessions cannot change the data in the affected rows. We make all pending changes permanent by using the commit statement. Here is what happens after a commit statement. Data changes are written to the database. The previous state of the data is no longer available within normal SQL queries. All sessions can view the results of the transaction. The locks on the affected rows are released. The rows are now available for other sessions to perform new data changes. All save points are erased. In this example in the slide, a row is deleted from the employees table and a new row inserted into the departments table. These changes are saved by issuing the commit statement. To demonstrate the commit statement, we will first delete 2 departments from the departments table, and we will update one employee's department ID. Once we have executed all the DML statements in this transaction, we will issue the commit statement to make these changes permanent in the database. Let's view the data that we're going to delete and update. First, we'll select from the departments table where the department ID is equal to 290 and 300. In our query result, we can see the detail of these 2 department IDs. We are going to delete these 2 department IDs. Next, let's view the row in our employees table. We are going to update the department ID for employee ID 206. Let's start our transaction and issue these DML statements. To delete the rows from the departments table, we will delete from the departments table where the department ID is in, and we're going to delete 290 and 300. Let's execute this delete statement. In the script output, we can see 2 rows have been deleted. The next DML statement in our transaction, we're going to update the employees table. We will set the department ID equal to 80, where the employee ID is equal to employee ID 206. Let's execute this update statement, and we can see that 1 row has been updated. To make these changes permanent in the database and to end our transaction, we issue the commit statement. In the script output, we can see the commit is complete. You have now learned about the state of the database before and after issuing the commit SQL command within your database. Describing the state of the database before and after issuing a rollback SQL command within the database. Every data change made during the transaction is temporary until the transaction is committed or rolled back. The state of the data before the rollback statement is issued can be described as follows. Data manipulation operations primarily affect the database buffer. Therefore, the previous state of the data can be recovered. The current session can review the results of the data manipulation operations by querying the tables. Other sessions cannot view the results of the data manipulation operations. The Oracle server institutes read consistency to ensure that each session sees data as it existed at the last commit. The affected rows are locked. Other sessions cannot change the data in the affected rows. We discard all pending changes used by the rollback statement, and this results in the following. Data changes are undone. The previous state of the data is restored, and the locks on the affected rows are released. While attempting to remove a record from the test table, you may accidentally empty the table. You can, however, correct this mistake and reissue a proper statement by using the rollback statement. Once your changes are complete, you can issue the commit statement to make the data change permanent. A part of a transaction can be discarded through an implicit rollback if a statement execution error is detected. If a single DML statement fails during the execution of a transaction, it is undone by a statement-level rollback. The Oracle server implements an implicit save point. The changes made by the previous DML statements in the transaction are not discarded. They can be committed or rolled back explicitly by the user. The Oracle server issues an implicit commit before and after any DDL statement. So even if your DDL statement does not execute successfully, you cannot roll back the previous statement because the server issued a commit. Terminate your transactions explicitly by executing a commit or rollback statement. To demonstrate the rollback statement, we have created the copy_m table, which is a copy of the employees table. We will accidentally delete all the rows from the copy_m table. When we realize we did this in error, we will issue a rollback statement to undo the data changes. First, we will select the rows from the copy_m table. In the query result, we can see the rows that currently exist in our copy_m tables. Let's now issue the delete statement. The script output shows 110 rows have been deleted. Let's select from our copy_m table to view the impact of the delete statement only in our current session. In our query result, we now see there are 0 rows in the copy_m table. We realize this delete statement was issued in error. To discard the delete statement, we issue the rollback statement. Let's execute our rollback statement. In the script output, it shows rollback complete. Let's now select from our copy_m table. In the query result, we can see we once again have the data in our copy_m table. By issuing the rollback statement, we undid the data changes that were made by the delete statement. You have now learned about the state of the database before and after issuing a rollback SQL command within your database. In this video, we will describe what read consistency is and its role in the database. Database users access the database in 2 ways: read operations in the form of a select statement and write operations in the form of update, insert, and delete statements. Read consistency is needed so that the following occurs. The database reader and writer are ensured a consistent view of the data. Readers do not view data that is in the process of being changed. Writers are ensured that the changes to the database are done in a consistent manner. Changes made by one writer do not disrupt or conflict with the changes made by another writer. Read consistency ensures that on the same data, readers do not wait for writers, writers do not wait for readers, and writers wait for writers. The purpose of read consistency is to ensure that each user sees data as it existed at the last commit, before a DML operation started. Note, the same user can log into different sessions. Each session maintains read consistency, even if it is the same user. Read consistency is an automatic implementation. It keeps a partial copy of the database in undo segments. The read consistent image is constructed from the committed data in the table and the old data that is being changed and that is not yet committed from the undo segment. When an insert, update, or delete operation is made on the database, the Oracle server takes a copy of the data before it is changed and writes it to an undo segment. All readers, except the one who issued the change, see the database as it existed before the change started. They view the undo segment's snapshot of the data. Before changes are committed to the database, only the user who's modifying the data sees the database with the alterations. Everyone else sees the snapshot in the undo segment. This guarantees that the readers of the data read consistent data that is not currently undergoing change. When a DML statement is committed, the change made to the database becomes visible to anyone issuing a select statement after the commit is done. The space occupied by the old data in the undo segment file is freed for reuse. If the transaction is rolled back, the changes are undone. The original, older version of the data in the undo segment is written back to the table. All users see the database as it existed before the transaction began. In this video, we have described what read consistency is and its role in the database. Using the for update clause in a SQL statement. When you issue a select statement against the database to query some records, no locks are placed on the selected rows. In general, this is required because the number of records locked at any given time is, by default, kept to the absolute minimum. Only those records that have been changed but not yet committed are locked. Even then, for the rows that are locked, others will be able to read those records as they appeared before the change. The before image of the data. There are times, however, when you may want to lock a set of records even before you change them in your program. Oracle offers the for update clause of the select statement to perform this locking. When you issue a select for update statement, the relational database automatically obtains exclusive row-level locks on all the rows identified by the select statement, thereby holding the records for your changes only. No one else will be able to change any of these records until you perform a rollback or a commit. You can append the optional keyword "no-wait" to the for update clause to tell the Oracle server not to wait if the table has been locked by another user. In this case, control will be returned immediately to your program or to your SQL Developer environment so that you can perform other work or simply wait for a period before trying again. Without the no wait clause, your process will block until the table is available. When the locks are released by the other user through the issue of a commit or rollback command. In the example in the slide, the statement locks the rows in the employees table who have a job ID set to st_clerk and where their location ID is set to 1500. It also locks rows in the departments table for departments with the location ID set to 1500. You can use the for update of column name to qualify the columns that you intend to change. The of list of the for update clause does not restrict you to changing only those columns of the selected rows. Locks are still placed on all rows if you simply state for update in the query and do not include one or more columns after the of keyword. The database will lock all identified rows across all tables listed in the from clause. To demonstrate the for update clause in a select statement, we have two SQL Developer sessions open. In the SQL Developer session on the left, we're going to update the employees table and we're going to set the department ID equal to 60 where the job ID is equal to SA_rep. Our session on the right, we have a select statement with the for update clause. We will wait 15 seconds should the rows be locked by another session. To start, let's issue our update statement. In the script output, we can see 32 rows have been updated. As we have not issued a commit or a rollback, these rows are locked. If we now issue the select for update statement in our session on the right, this session will hang until we issue a commit or a rollback in the session on the left. As you could see, when we executed the rollback statement, we showed that the rollback was complete. The locks on these rows were released. As soon as the locks on these rows were released, these rows became available in the select for update statement. If we now try and update these rows again, this session will hang as the rows are currently locked by our session on the right. Let's issue the update statement. We can see in our session on the left, the session is hanging. Let's roll back this statement, our select for update statement. The moment we issue the rollback and end the transaction, the rows are updated in the session on the left. You are now ready to use the for update clause in your SQL select statements. Now that you've learned how to process a database transaction, it is time to put that knowledge to work. In this exercise, you will delete Betty Danks from the my_employee table and confirm your changes to the table. You will then commit all pending changes. Next, you will insert a new row into the my_employee table, and you will then mark an intermediate point in the processing of the transaction. The next SQL statement, you will delete all rows from the my_employee table and confirm that the table is empty. For the next task, you will discard the most recent delete operation without discarding the earlier insert operation and confirm that the new row is still intact. You will then make the data addition permanent. For the last task, you will remove all rows from the my_employee table using the truncate statement. For this exercise, you will first need to create and populate the my_employee table from the provided create script. When you are ready, pause this video and perform the exercise. When you are done, come back to the video and I will work through the exercise with you. Before starting with the tasks in this exercise, we need to create and populate the my_employee table. Make use of the create script provided to create and populate the table. Let's execute the script. In our script output, we can see that our table has been created and the rows inserted. We will issue a commit statement to ensure these changes are made permanent in the database. For the first task, we will delete Betty Danks from the my_employee table, and we will then confirm the changes to the table. Our delete statement will look as follows. Delete from my_employee where the last name is equal to Danks. Let's execute our delete statement. In our script output, we can see one row has been deleted. Next, we will select from the table to ensure that this row has been deleted. We can see in the query result, the employee with the last name Danks has been deleted. To make these changes permanent, we will issue the commit statement. For the next task, we will insert a new employee into the my_employee table. Let's execute this insert statement. We now need to mark an intermediate point in the processing of the transaction. To do this, we will issue the save point command. We will give our save point a name. We will call it step 3. Let's create this save point. In our script output, we can see we now have a save point step 3. In this transaction, our next action is to delete all rows from the my_employee table and to confirm that the table is empty. Our delete statement, delete from my_employee. Let's execute this statement. And if we then select from the my_employee table to view the rows, we can see there are 0 rows in the table. We realize the delete of all the rows from the my_employees table was issued in error, and we need to roll back only the delete statement. To do this, we will roll back to the save point step_3 that we created. The statement roll back to step_3. Let's execute this rollback statement. In the script output, we can see the rollback is complete. Let's select from our table. In the query result, we can see the delete of the rows has been rolled back. We can also see that the insert statement is still valid. To make this change permanent in the database, we issue the commit statement. For the final task, we will remove all rows from the my_employees table by using the truncate statement. Let's first select to view the rows in our table. In the query result, we can see there are 5 rows in our table. Let's issue our truncate table statement. The script output confirms the table has been truncated. Let's now select from the table again. We can see in the query result that there are now 0 rows in the my_employee table. In this video, we will describe the types of set operators and their associated guidelines. Set operators are used to combine the results of 2 or more component queries into one result. Queries containing set operators are called compound queries. The list of set operators consists of the union operator. The union operator returns rows from both queries after eliminating duplications. The union all operator returns rows from both queries, including all duplications. The intersect operator returns rows that are common to both queries. The minus operator returns rows in the first query that are not present in the second query. All set operators have equal precedence. If a SQL statement contains multiple set operators, the Oracle server evaluates them from left top to right bottom, if no parentheses explicitly specify another order. Use parentheses to specify the order of evaluation explicitly in queries that use the intersect operator with other set operators. The expressions in the select lists of the queries must match in number and data type. Queries that use union, union all, intersect, and minus operators must have the same number and data type of columns in their select list. The data type of the columns in the select list of the queries in the compound query may not be exactly the same. The column in the second query must be in the same data type group, such as a numeric or character data type, as the corresponding column in the first queries. We can use set operators in subqueries. You should use parentheses to specify the order of evaluation in queries that use the intersect operator with other set operators. This ensures compliance with emerging SQL standards that will give the intersect operator greater precedence than the other set operators. The order by clause can appear only at the very end of the SQL statement. In this video, we've described the types of set operators and their associated guidelines. Recognizing how the Oracle server manages set operators. When a query uses set operators, the Oracle server eliminates duplicate rows automatically, except in the case of the union all operator. The column names in the output are decided by the column list in the first select statement. By default, the output is sorted in ascending order of the first column of the select clause, except in a union all. The corresponding expressions in the select list of the component queries of a compound query must match in number and data type. If component queries select character data, the data type of the return values is determined as follows. If both queries select values of char data type of equal length, the return values have the char data type of that length. If the queries select values of char with different lengths, the return value is varchar 2 with the length of the larger char value. If either or both of the queries select values of varchar 2 data type, the return values have the varchar 2 data type. If component queries select numeric data, the data type of the return value is determined by numeric precedence. If all queries select values of the number type, the return values have the number data type. In queries using set operators, the Oracle server does not perform implicit conversion across data type groups. Therefore, if the corresponding expressions of component queries resolve to both character data and numeric data, the Oracle server will return an error. When learning about set operators, there are two tables that we will be working with. The first is the employees table. You are already familiar with the employees table that stores employee details such as unique identification number, email address, job identification such as ST clerk, salary, manager, and so on. The next table is the retired employees table. The retired employees table stores the details of employees who have left the company. To display the structure and data of the employees and the retired employees table, we are logged into our HR connection in SQL Developer. First, we will describe the structure of the employees table. In the script output, we see the column names and data types that make up the employees table. Let's select from the employees table. In the query result, we can see the data that is stored in the employees table. Let's now describe the retired employees table. In the script output, we can see the columns and data types that make up the retired employees table. Let's now select the data from the retired employees table. In the query result, we can see the rows that exist in the retired employees table. Now you know how to recognize how the Oracle server manages set operators in a SQL statement, and we have described the tables that will be used when learning about the set operators. Using the union and union all operators to return all rows in a SQL statement. The union operator returns all rows that are selected by either query. Use the union operator to return all rows from multiple tables and eliminate any duplicate rows. Some guidelines when working with the union and union all operators. The number of columns being selected must be the same. The data types of the columns being selected must be in the same data type group, such as numeric or character. The names of the columns need not be identical. Union operates over all the columns being selected. Null values are not ignored during duplicate checking. By default, the output is sorted in ascending order of the columns of the select clause. The example in this slide displays the job details for all current and retired employees. Duplicate records are eliminated. If records that occur in both the employees and retired employees tables are identical, the rows are displayed only once. We use the union all operator to return all rows from multiple queries. Guidelines when using the union all operator. The guidelines for union and union all are the same, with the following two exceptions that pertain to the union all operator. Unlike the union operator, duplicate rows are not eliminated, and the output is not sorted by default. In this example, we make use of the union all operator. The union all operator does not eliminate duplicate rows and returns all rows selected by either query, including duplicates. We are in our SQL worksheet window, and we have the SQL statement as displayed in the union all example slide. Let's execute this statement and review its output. In the query result, we can see that all rows from both tables are returned. This results in duplicate rows being returned. If we now update this SQL statement to make use of the union operator, let's execute this statement. In the query result, only the distinct rows have been returned. Duplicate rows have been eliminated. You are now ready to start using the union and union all set operators in your SQL statements. In this video, we will learn how to use the intersect operator to return all rows that are common to multiple queries in a SQL statement. The intersect operator is used to return all rows that are common to multiple queries. Some guidelines when working with the intersect operator. The number of columns and the data types of the columns being selected by the select statements in the queries must be identical in all the select statements used in the query. The names of the columns, however, need not be identical. Reversing the order of the intersected tables does not alter the result. Intersect does not ignore null values. In the example in this slide, the query returns only those records that have the same values in the selected columns in both tables. Taking the example from the slide, let's execute this statement. In the query result, we can see that Manager ID 101 in Department ID 100 and Manager ID 149 in Department 80 are the only two records that have the same values in the selected columns in both tables. Next, we would like to create a report that lists the employee IDs for all employees who are purchasing clerks and who work in Department 30. Our SQL statement will look as follows. We will select the employee ID from the employees table where the job ID is equal to a purchasing clerk. We then specify intersect and our second SQL statement. We select the employee ID from the employees table where the department ID is equal to Department 30. Let's execute this statement and review its output. In the query result, we can see the employee IDs returned for the purchasing clerks who work in Department 30. And that is how we use the intersect operator to return all rows that are common to multiple queries in a SQL statement. Using the minus set operator to return all distinct rows selected by the first query but not present in the second query result set. The first select statement minus the second select statement. Note, the number of columns must be the same and the data types of the columns being selected by the select statements in the queries must belong to the same data type group in all the select statements used in the query. The names of the columns, however, do not need to be identical. The example in the slide displays the employee IDs and job IDs of those employees who work in the sales department. The employee IDs in the retired employees table are subtracted from those in the employees table. The result set displays the employees remaining after the subtraction, and they are represented by rows that exist in the employees table, but do not exist in the retired employees table. These are the records of the employees who work in the sales department. To demonstrate the use of the minus set operator, we are logged into our HR connection in SQL Developer. We would like to view a list of departments from the Departments table for which there are no entries in the Employees table. Our SQL statement will look as follows. We will select the Department ID from the Departments table minus we select Department ID from the Employees table. Let's execute this statement and review the output. In the query result, we return a list of all department IDs which exist in the Departments table, but for which there are no employees assigned in the Employees table. In this video, we've covered using the minus set operator to return all distinct rows selected by the first query but not present in the second query result set. In this video, we will describe how the expressions in the select list of the queries must match in number in a SQL statement when working with set operators. Because the expressions in the select list of the queries must match in number, you can use dummy columns and the data type conversion functions to comply with this rule. To match the column list explicitly, you can insert null columns at the missing positions so as to match the count and data type of selected columns in each select statement. In the slide, the name warehouse location is given as the dummy column heading. The toChar function is used in the first query to match the varchar2 data type of the state province column that is retrieved by the second query. Similarly, the toChar function in the second query is used to match the varchar2 data type of the department name column that is retrieved by the first query. The employees and retired employees tables have several columns in common. For example, employee ID, job ID, and department ID. What if you want the query to display the first name, job ID, and hire date using the union operator, knowing that the hire date exists only in the employees table? The code example in the slide matches the first name and job ID columns in the employees and retired employees tables. Null is added to the retired employees select statement to match the hire date column in the employees select statement. In the result shown in the slide, each row in the output that corresponds to a record from the retired employees table contains a null in the hire date column. In this demonstration, we will make use of the SQL statement presented in the first slide. We select the location ID, department name, and we include the dummy warehouse location as a null column, as this column does not exist in the departments table. We then include the union keyword, and in our second SQL statement, we select the location ID, we specify the dummy department column as it does not exist in the locations table, and we include the state province column. Let's execute the SQL statement and review the output. In the query result, where the dummy column was specified, a null value is returned. In this video, we have described how the expressions in the select list of the queries must match in number in a SQL statement when working with set operators. Using the order by clause in set operations in a SQL statement. The order by clause can be used only once in a compound query. If used, the order by clause must be placed at the end of the query, and the order by clause accepts a column name or an alias. Note, the order by clause does not recognize the column names of the second select query. By default, the output is sorted in ascending order in the first column of the first select query. To avoid confusion over column names, it is a common practice to order by the column position. You cannot use the columns from the second query to sort the output. To demonstrate the order by clause in a set operation, we will select from the employees and the retired employees table, and we will order the data by the job ID column from the first query. Our SQL statement will look as follows. We will select the employee ID, the job ID, and the salary from the employees table. We'll specify the union keyword. We will then select the employee ID, the job ID, and as there is no salary column in the retired employees table, we will pass a 0. We're selecting from the retired employees table, and we will order by column number 2. Let's execute this statement and review the output. In the query result, we can see the data is sorted by the job ID column from the first SQL statement. You now know how to use the order by clause in a set operation in a SQL statement. Now that you've learned how to write reports using the set operators, it is now time to put that knowledge to work. In this exercise, you will use the set operators to create a report that lists the department IDs for departments that do not contain the job ID st_clerk. In the next task, you will use the set operators to create a report that provides a list of countries that have no departments located in them. For the last task in this exercise, you will create a report with the following specifications: the last names and department IDs of all employees from the employees table, regardless of whether they belong to a department, and include the department IDs and department names of all departments from the departments table, regardless of whether they have employees working in them. Write a compound query to accomplish this report. When you are ready, pause this video and perform the exercise. When you are done, come back to the video and I will work through the exercise with you. We are connected to our HR connection in SQL Developer. For the first task in this exercise, we need to create a report that lists department IDs for departments that do not contain the job ID st_clerk. We will use the -set operator. Our SQL statement looks as follows. We select the department ID from the departments table. We use the minus operator and we select the department ID from the employees table where the job ID is equal to st_clerk. Let's execute this SQL statement now. The output in the query result returns a list of department IDs for departments that do not contain the job ID st_clerk. In this next task, we will use the set operators to create a report that provides a list of countries that have no departments located in them. We are once again using the -set operator. Our SQL statement looks as follows. We select the country ID and the country name from the countries table. We then include the minus operator, and in our second SQL statement, we need to join the countries table to the locations table, and we then join the locations table to the departments table. This is because there is no direct link between the departments and the countries tables. The SQL statement reads, we select the country ID from the locations table and the country name from the countries table. We select from the locations table and we join to the countries table on the country ID. We then join to the departments table where the location ID in the departments table is equal to the location ID in the locations table. Let's execute our SQL statement. In the query result, the output provides a list of countries that have no departments located in them. For this final task, using a compound query, we need to create a report to return the last name and department IDs of all employees from the employees table, regardless of whether they belong to a department or not. We also need to return the department IDs and department names of all departments from the departments table, regardless of whether they have employees working in them. Our SQL statement looks as follows. We select the last name, department ID, and as we have no department name in our employees table, we've passed a function, the toChar function, and we've passed a null value from the employees table. We have made use of the union operator, and in our second SQL statement, we select, as we have no last name in our departments table, we've used the toChar function to pass a null value. We've included the department ID and department name, selecting from the departments table. The number of columns in both queries needs to be the same. Let's execute the SQL statement. The union operator joins all the rows from the first SQL statement to all the rows from the second SQL statement. Let's execute this statement. In our query result, we'd return a list of all employees' last names and department IDs from the employees table, regardless of whether they belong to a department. We also include a list of departments, including the department IDs and department names for all departments from the departments table, regardless of whether they have employees working in them. In this video, we will describe the data definition language database objects and their associated naming rules. Data definition language is also known as DDL. The Oracle database can contain multiple data structures. Each structure should be outlined in the database design for it to be created during the build stage of database development. A table stores data. A view is a subset of data from one or more tables. A sequence generates numeric values. An index improves the performance of some queries. A synonym gives an alternative name to an object. When working with table structures, tables can be created at any time, even when users are using the database. You do not need to specify the size of a table. The size is ultimately defined by the amount of space allocated to the database as a whole. It is important, however, to estimate how much space a table will use over time. Table structures can be modified online. Note, more database objects are available but are not covered in this video. Database tables and columns are named according to the standard rules for naming any Oracle database object. Table names and columns must begin with the letter. They must be 1 to 30 characters long. Names must contain only the characters capital A to Z, lowercase a to z, 0 to 9, the underscore, the $sign, and the pound sign. These are legal characters, but their use is discouraged. Names must not duplicate the name of another object owned by the same Oracle Server user. Names must not be an Oracle Server reserved word. You may also use quoted identifiers to represent the name of an object. A quoted identifier begins and ends with double quotation marks. If you name a schema object using a quoted identifier, you must use the double quotation marks whenever you refer to that object. Quoted identifiers can be reserved words, but this is not recommended. For more information, see the Schema Object Names and Qualifiers section in the Oracle Database SQL Language Reference for 12c database. When naming objects, use descriptive names for tables and other database objects. Names are not case sensitive. If we look at the first 4 SQL statements, we reference the employees table in 4 different ways. First in lowercase, then in uppercase, then with most letters in lowercase and some in uppercase, and then most letters in uppercase and some in lowercase. Let's execute these statements. We can see that each of these statements executes successfully. This is because the name is not case sensitive. Quoted identifiers are, however, case sensitive. Let's test these examples, where we've specified the employees with various cases and in double quotes. For our first select statement, we receive an error that the table of view does not exist. Let's test the employee's name in lowercase. We receive the same error that the table of view does not exist. Let's issue our last select statement where the employees is in uppercase. This SQL statement executes successfully. Quoted identifiers are case sensitive. In this video, we have described the data definition language database objects and their associated naming rules. Using the Create Table SQL command to create new tables in the database. Tables are created to store data. To create a table, we execute the SQL Create Table statement. This statement is one of the DDL statements that are a subset of the SQL statements used to create, modify, or remove database structures. These statements have an immediate effect on the database, and they record information in the data dictionary. To create a table, A user must have create table privilege and a storage area in which to create objects. The database administrator uses the data control language statements to grant privileges to the users. Looking now at the create tables syntax, you specify a schema. This is the same as the owner's name. The table is the name of the new table that you wish to create. The default expression specifies a default value if a value is omitted in the insert statement. The column is the name of the column, and the data type is each column's data type and length. Note, the create any table privilege is needed to create a table in any schema other than the user's schema. The example in this slide creates the dep table with 4 columns: depno, dname, lock, and create date. The create date column has a default value. If a value is not provided for an insert statement, the system date is automatically inserted. To confirm that the table was created, we use the describe command. As the create table statement is a DDL statement, an automatic commit takes place when this statement is issued. We are in our SQL Developer session and connected to our HR schema. We will create a new table owned by our HR user, and it will be called job_archive. We will include a default value for the job_arc_date column in the table. Let's review the syntax for creating the table. We specify create table. We have included the schema name and our new table, which is jobs_archive. Then, in brackets, we've included the columns that we're going to create, including their data types and their length. We have a job ID column, a job title, a min salary, a max salary, and the job arc date. We have included a default value for this column. Should no value be included during the insert statement, the system date will be inserted. Let's create this table. We can see in the script output that the table is created. To view the definition of the table, we can do a describe of this table. We will specify describe and then the table name. In the script output, we can see the definition of our table, including its columns and data types. Within our Oracle database, we have a data dictionary. Our data dictionary contains views, and these views store information about database objects, such as tables, views, indexes, and so on. We can view a list of the tables that we as the HR user own by querying the data dictionary. To do this, we can select table name from user_tables, and we will sort our data by table name. The users_tables dictionary view stores information about the tables in our current user session. Let's execute this SQL statement. In our query result, we can see a list of all the tables that are owned by the HR user. You now know how to use the create table SQL command to create a new table in the database. Different Oracle database data types are used when creating a table, and in this video, we will describe these data types. When you identify a column for a table, you need to provide a data type for the column, and there are several data types available. The first is varchar2. Varchar2 consists of variable length character data. The minimum size is 1, with the maximum size 32767 bytes. A maximum size must be specified. Next is the char data type. This is the default. It contains fixed length character data of length size bytes. The minimum size is 1 and the maximum size is 2000. The number data type consists of variable length numeric data having precision and scale. Precision is the total number of decimal digits, and scale is the number of digits to the right of the decimal point. Precision can range from 1 to 38, and scale can range from -84 to +127. The date data type consists of date and time values to the nearest second between January the 1st, 4712 BC and December the 31st, 9999 AD. The long data type contains variable length character data up to 2 gig. A club is a character large object containing single byte or multiple byte characters. An enclub, a character large object containing Unicode characters. Both fixed width and variable width character sets are supported, both using the database national character set. The raw data type contains raw binary data of length size bytes. You must specify a size for a raw value. The maximum size is 32767 bytes. Long raw consists of raw binary data of variable length up to 2 gigabytes. A blob is a large binary object. A B file contains binary data stored in an external file up to 4 gigabytes. A row ID data type. This data type is primarily used for values returned by the row ID pseudo-column. Some guidelines when making use of the long data type. A long column is not copied when a table is created using a subquery. A long column cannot be included in a group by or an order by clause. Only one long column can be used per table. No constraints can be defined on a long column. You may want to use a club column rather than a long column. There are several date-time data types that are available. The first, timestamp, enables the storage of time as a date with fractional seconds. It stores the year, month, day, hour, minute, and second value of the date data type, as well as the fractional seconds value. There are several variations of this data type, such as with time zone and with local time zone. The next data type is interval year to month. This enables the storage of time as an interval of years and months. It is used to represent the difference between two date-time values in which the only significant portions are the year and month. The interval day to second data type enables storage of time as an interval of days, hours, minutes, and seconds, used to represent the precise difference between two date-time values. For more information about the date-time data types, see the sections for each data type in the Oracle Database SQL Language Reference for 12c database. In this video, we've described the different Oracle Database data types which are available to be used when identifying a column for a new table. Defining a default value to be assigned to a column when creating a table. When you define a table, you can specify that a column should be given a default value by using the default option. This option prevents null values in a column when a row is inserted without including a value for the column in the insert statement. The default value can be a literal, an expression, or a SQL function, such as sysdate or user. The value cannot be the same name of another column or a pseudo-column, such as nextVal. The default expression must match the data type of the column. To demonstrate the use of a default value being assigned to a column, we will create a table and insert data into the table. The table we're going to create is the hire_dates table. It will consist of two columns, the ID column of data type number and the hire_date column of data type date, and we will pass the sysdate as the default should no value be included in the insert statement. Let's create our hire_dates table. Our table has been created. Next, we're going to insert a row into the hire_dates table. We will pass a value for the ID column and we will pass null for the hire_date column. Let's execute this insert statement. If we select from the hire_dates table to view our row, we can see that the hire_date column contains a null value. The reason for this is because we passed a null value for the column in the insert statement. Next, we're going to insert another row into the hire_dates table, and this time we're going to specify the ID column and pass only a value for the ID column. Let's execute this insert statement. We can see that another row has been inserted. Let's select from our table. In the query result, we can see the second row has been inserted into our table. And as we did not specify a value for the hire_date column, the default sysdate has been inserted. You have now learned how to define a default value to be assigned to a column when you create a table. Identifying the different types of constraints and how these are used to enforce rules at a table level. The Oracle server uses constraints to prevent invalid data entries into tables. Constraints can be used to do the following: enforce rules on the data in a table, whenever a row is inserted, updated, or deleted from that table. The constraint must be satisfied for the operation to succeed. Constraints ensure the consistency and integrity of the database. They prevent the dropping of a table if there are dependencies from other tables. It also provides rules for Oracle tools, such as SQL Developer. The data integrity constraints consist of not null. Not null specifies the column cannot contain a null value. The unique constraint specifies a column or combination of columns whose values must be unique for all rows in the table. The primary key constraint uniquely identifies each row of that table. The foreign key constraint establishes and enforces a referential integrity between the column and a column of the reference table, such that the values in one table must match the values in another table. Lastly, the check constraint. The check constraint specifies a condition that must be true. All constraints are stored in the data dictionary. Constraints are easy to reference if you give them a meaningful name. Constraint names must follow the standard object naming rules, except that the name cannot be the same as another object owned by the same user. If you do not name your constraint, the Oracle server generates a name with the format sys_c followed by an integer. This is to ensure that the constraint name is unique. Constraints can be defined at the time of table creation or after the creation of the table. You can define a constraint at the column or table level. Functionally, a table level constraint is the same as a column level constraint. Constraints can be viewed in the data dictionary. For more information, see the section on constraints in the Oracle Database SQL Language Reference for 12c database. In this video, we've covered the different types of constraints and guidelines for creating constraints, and we've looked at how these constraints are used to enforce rules at a table level. In this video, we will describe the syntax for defining constraints when creating a table. You can create constraints at either the column level or the table level. Constraints defined at the column level are included when the column is defined. Table level constraints are defined at the end of the table definition and must refer to the column or columns on which the constraint pertains. It is included in parentheses. It is mainly the syntax that differentiates the two. Otherwise, functionally, a column-level constraint is the same as a table-level constraint. Not null constraints can be defined only at the column level. Constraints that apply to more than one column must be defined at the table level. Looking at the syntax for the create table statement, the schema is the same as the owner's name. The table is the name of the new table. The default expression specifies a default value, which will be used if the value is omitted during the insert statement. We then specify the name of the column and the data type. This is the column's data type and length. The column constraint is an integrity constraint as part of the column definition. The table constraint is an integrity constraint as part of the table definition. Constraints are usually created at the same time as the table, but constraints can be added to a table after its creation. They can also be temporarily disabled. Both examples in the slide create a primary key constraint on the employee ID column of the employees table. The first example uses the column-level syntax to define the constraint. The second example uses the table-level syntax to define the constraint. We will cover each of the constraints in more detail in future videos. We are in our SQL Developer session, and in our SQL Worksheet window, we have a Create Table script. In our Create Table script, we create a table called hire_dates. In this table, we define a column ID with the number data type. We then define a hire_date column of date data type. We include a column level constraint called hire_date_NN. This is a not null constraint. We then include a table level constraint. We've given it the name ID_PK. It is a primary key constraint defined on the ID column. Let's create this table. In the script output, we can see that we have created the hire_dates table. Let's look at the definition of our table by doing a describe. In the script output, we can see that we have two columns in our table. Both columns are defined as not null. The hire date is defined as not null, as we specified this column level constraint when we created the table. The ID column has a not null constraint. This is due to us creating a primary key constraint on this column. A primary key column cannot have null values. Let's query the data dictionary to view the constraints on our table. To do this, we are selecting the constraint name, the constraint type, and the table name from the user constraints view, where the table name is equal to our hire_dates table. Let's execute this select statement. In the query result, we can see that on our hire_dates table, we have two constraints defined. The first is the primary key constraint, and the second is the check constraint, to ensure that null values are not inserted into the hire_date column. In this video, we have described the syntax for defining constraints when creating a table. In this video, we will describe the use of the not null and primary key constraints. The not null constraint ensures that the column contains no null values, and not null constraints must be defined at the column level. Columns without the not null constraint can contain null values by default. In the employees table displayed in the slide, the employee ID column inherits a not null constraint because it is defined as a primary key. The last name, email, hire date, and job ID columns have the not null constraint enforced on them. The remaining columns can contain null values by default. A primary key constraint creates a primary key for the table. Only one primary key can be created for each table. The primary key constraint is a column or set of columns that uniquely identifies each row in the table. This constraint enforces the uniqueness of the column or column combination and ensures that no column that is part of the primary key can contain a null value. Note, because uniqueness is part of the primary key constraint definition, the Oracle server enforces the uniqueness by implicitly creating a unique index on the primary key column or columns. We will create a new table called departments_archive in the HR schema to demonstrate creating a primary key and defining not null constraints. Our create table syntax will look as follows. We will create table hr.departments_archive. We will then define our columns. Our first column is dept_id of data type number. Our next column is department name. We will make this column a varchar 2 of length 30, and we will define a not null. This column cannot contain a null value. Our next column is the manager ID column of number data type. We then define the location ID column, also number data type. We will also include the not null constraint on this column. Lastly, we're going to define a constraint at the table level. We will call it dept ID arc pk. This is a primary key constraint, and our primary key constraint will be defined on our dept ID and our manager ID column. These two columns need to be unique for this table. Let's create our table. In the script output, we can see that our table has been created. Let's now do a describe on our table. In the script output, we can see that all the columns are defined as not null. The reason for this is the department name column and the location ID columns. We define not null constraints explicitly on these columns. For the dept ID and the manager ID columns, these two columns make up the primary key, and a primary key column cannot contain a null value. We have drilled down to our department's archive table, and if we look at the constraints column, we can see the constraints defined on this table. We have a primary key constraint defined, and we have two check constraints. These constraints ensure that the department name and location ID columns cannot contain null values. You are now ready to make use of the not null and primary key constraints when creating your tables. In this video, we will describe the use of the unique constraint when creating a table. A unique key integrity constraint requires that every value in a column or set of columns be unique. That is, no two rows of a table can have duplicate values in a specified column or set of columns. The column or set of columns included in the definition of the unique key constraint is called the unique key. If the unique constraint comprises more than one column, that group of columns is called a composite unique key. Unique constraints enable the input of nulls, unless you also define not null constraints for the same columns. In fact, any number of rows can include nulls for columns without the not null constraints, because nulls are not considered equal to anything. A null in a column or in all columns of a composite unique key always satisfies a unique constraint. Note, because of the search mechanism for the unique constraints on more than one column, you cannot have identical values in the non-null columns of a partially null composite unique key constraint. Unique constraints can be defined at the column level or at the table level. You define the constraint at the table level when you want to create a composite unique key. A composite key is defined when there is not a single attribute that can uniquely identify a row. In that case, you can have a unique key that is composed of two or more columns, the combined value of which is always unique and can identify rows. The example in this slide applies the unique constraint to the email column of the employees table. The name of the constraint is emp_email_UK. Note, the Oracle server enforces the unique constraint by implicitly creating a unique index on the unique key column or columns. To demonstrate creating a unique constraint when you create your table, we're going to create the departments_archive table. We will then insert rows into this table to demonstrate what should happen when you violate the unique constraint. In our departments_archive table, the location_ID column has been defined with a unique constraint, meaning that each row in the table must have a unique location ID. Let's create our table. Our table has been created. Let's now view the definition of the table. Click on Tables, right-click, click on Refresh, and we can view our department archive table. Click on the department underscore archive table, and the definition is displayed on the right. If we then click on the Constraints tab, we can see the constraints that have been created on this table. We can see a unique constraint has been created on the location underscore ID column. If we now click on the Indexes tab, we can see that the Oracle server has created a unique constraint implicitly on the location underscore ID column. We will now insert 2 rows into our departments underscore archive table. Let's insert the first row. 1 row has been inserted into the table. Let's now execute the second insert statement. When we execute this insert statement, we encounter the unique constraint violation error. This is because the location ID in the first insert statement is the same as in the second insert statement. We can only have one unique location ID. The location ID 100 can only exist once in this table. You now know how to use the unique constraint to define a unique column when creating a table. Defining a foreign key or referential integrity constraint when creating a table. The foreign key constraint designates a column or a combination of columns as a foreign key and establishes a relationship with a primary key or a unique key in the same table or a different table. In the example in the slide, the department ID has been defined as the foreign key in the employees table, which is the dependent or child table. The employee table references the department ID column of the departments table, also known as the referenced or parent table. Some guidelines when creating a foreign key constraint. A foreign key value must match an existing value in the parent table, or it must be null. Foreign keys are based on data values and are purely logical, rather than physical pointers. Foreign key constraints can be defined at the column or table constraint level. A composite foreign key must be created by using the table level definition. The example in this slide defines a foreign key constraint on the department ID column of the employees table, using the table level syntax. The foreign key can also be defined at the column level, provided that the constraint is based on a single column. The syntax differs in that the keywords foreign key do not appear. Foreign key is used to define the column in the child table at the table constraint level. References identifies the table and the column in the parent table. On-delete cascade indicates that when a row in the parent table is deleted, the dependent rows in the child table are also deleted. On-delete set null indicates that when a row in the parent table is deleted, the foreign key values are set to null. The default behavior is called restrict rule. This disallows the update or deletion of reference data. Without the on-delete cascade or the on-delete set null options, the row in the parent table cannot be deleted if it is referenced in the child table. These keywords cannot be used in column-level syntax. For this demonstration, we will create the departments underscore archive table. Should this table already exist, use the following command to drop the table first. Drop table followed by hr.departments underscore archive. Let's execute the drop table statement. And in the script output, we can see that the table has been dropped. In our create table script, we have the following constraints defined. We have a unique constraint on the location ID column. We have a primary key constraint defined on the department ID and the manager ID columns. And we have a foreign key constraint defined on the location ID column, referencing the locations table, location ID column. Let's create our table. In the script output, we can see that our table has been created. To view the constraints defined on our created table, let's view the table's definition. We click on Tables, we click on Departments underscore archive, and on the right we will see the table definition. Let's click on the Constraints tab. In the Constraints tab, we can see all the constraints that have been created for this table. We can see our foreign key constraint has been defined on the Locations table. The delete rule by default is set to no action. We are not able to delete or update a row in the parent table for which a row exists in the child table. And that is how we define a foreign key constraint when creating a new table. In this video, we will describe the use of the check constraint. The check constraint defines a condition that each row must satisfy. To satisfy the constraint, each row in the table must make the condition either true or, in the case of a null, unknown. You cannot reference columns from other tables. The condition can use the same constructs as the query conditions, except the queries that refer to other values in other rows. A single column can have multiple check constraints that refer to the column in its definition. There is no limit to the number of check constraints that you can define on a column. Check constraints can be defined at the column level or at the table level. We are going to create a table called teach_emp to demonstrate a check constraint. We can see on the left in connections that we already have a teach_emp table. First, we're going to drop this table. In our script output, we can see that we have dropped the teach_emp table. In our create table statement, our check constraint that we're going to create is on the cell column, and we're going to check for the cell greater than 0. If this constraint is violated, an insert statement will result in an error. Our create table will also create two not null constraints. This will create a check constraint on these columns to verify that nulls are not inserted into these two columns. Let's create our table. Our HR teach_emp table has been created. To view the constraints that have been created on the table, we can click on the teach_emp table. This will open up the definition for this table. If we then click on the Constraints tab, we can see a list of all the constraints that have been created on our teach_emp table. A second method for viewing the constraints on the teach_emp table is to query the dictionary view user_constraints. Let's execute the SQL statement. And in our query result, we can see a list of the constraints that have been created on the teach_emp table. To test the constraint we created on the cell column, we're going to insert two rows into our teach_emp table. Let's execute these insert statements. In the first insert statement, we encounter a check constraint violated error. This is because the value we included for the cell column violates the check constraint we configured on this table. Let's insert our second row into the table. We can see in the script output, one row has been inserted. This row does not violate the check constraint. Let's select from our table to view the data. In our query result, we can see that one row has been inserted into the teach_emp table. You are now ready to make use of the check constraint when creating a table to validate a condition when inserting data into the table. In this video, we will describe the conditions when a constraint is violated. When you have constraints in place on columns, an error is returned if you try to violate the constraint rule. For example, if you try to update a record with a value that is tied to an integrity constraint, an error is returned. In the example in this slide, Department 55 does not exist in the parent table Departments. You therefore receive Parent Key Not Found violation, error-02291. If you attempt to delete a record with a value that is tied to an integrity constraint, an error is returned. The example in the slide tries to delete Department 60 from the Departments table, but it results in an error because that department number is used as a foreign key in the Employees table. If the parent record that you attempt to delete has child records, you receive the child record found violation, ORA-02292. Should you attempt to delete a department for which there are no employees in that department, the statement will succeed. We will now demonstrate some conditions when a constraint is violated. To prepare the environment, first, we're going to drop the HR teach_emp table. Next, we will recreate this table using our create script. In the teach_emp table, we can see we have the following constraints. We have a primary key constraint, we have a not null constraint, we have a check constraint on the cell column, we have a second not null constraint, and we have a foreign key constraint to the department ID column in the departments table. Let's now insert a row into the teach_emp table. In the script output, we can see we encounter ORA-02290, a check constraint violation error. This is because the value we inserted for the cell column violates the check constraint. Let's insert the next row. In the script output, we can see one row is inserted. If we attempt to insert this row again, we now encounter an ORA-00001 unique constraint violated. This is because we have a primary key which forces uniqueness on the ID, and it cannot contain duplicate values. Next, we're going to delete a row from the departments table. If we issue our first delete statement, we encounter an ORA-02292 integrity constraint violated, child record found. This is because we have in our teach_emp table, we have a record with department 50. We are therefore not able to delete this department ID. Let's delete the next row from our departments table. We were able to delete department ID 400 successfully, as there were no constraints violated during the delete of this department ID. In this video, we've described and demonstrated the conditions when a constraint is violated during a DML on a table. Creating a new table and inserting rows at the same time by combining the create table and the as subquery option. A second method for creating a table is to apply the as subquery clause. This will create the table and insert rows from the subquery. The syntax is create table, followed by the name of the table, and then in brackets, the list of columns. We include the name of the column, a default value, and an integrity constraint. This is then followed by the subquery. The subquery is a select statement that defines the set of rows to be inserted into the new table. Some guidelines when creating a table using a subquery. The table is created with the specified column names, and the rows retrieved by the select statement are inserted into the table. If column specifications are given, the number of columns must be equal to the number of columns in the subquery select list. The column definition can contain only the name of the column and the default value. If no column specifications are given, the column names of the table are the same as the column names in the subquery. The column data type definitions and the not null constraint are passed to the new table. Note that only the explicit not null constraint will be inherited. The primary key column will not pass the not null feature to the new column. Any other constraint rules are not passed to the new table. You can, however, add constraints in the column definition. The example in this slide creates a table named Dept80, which contains details of all employees working in Department 80. Notice that the data for the Dept80 table comes from the employees table. You can verify the existence of a database table and check the column definitions by using the describe command. We need to create a new table called Manager 100, and the rows in this table must be a list of all employees who report to Manager 100 in the Employees table. Our Create table looks as follows. We will create table, followed by the schema and the new table name. We do not include any columns, therefore the column names will be the same as the columns in the select subquery. We include the as keyword and we then write our subquery. We're going to select the employee ID, the last name, the first name, the hire date, and the expression salary times 12. We would like the annual salary from the employees table where the manager ID is equal to 100. Let's create our table. In the script output, you can see we encountered an error when creating this table. This is because we defined an expression in our subquery and we need to provide a column alias when we define an expression. Let's update our create table statement. We will give it the column alias annual salary. Let's now create our table. We've updated the annual salary column alias. Let's now create our table. We can see that our Manager 100 table has been created. Let's execute a select statement from our new table to view the rows that have been inserted by the subquery. In our query result, we can see that we have 16 rows inserted into our new Manager 100 table. To view the definition of our new table, we issue the describe command and the table name. Let's execute our describe command. In the script output, we can see the definition of our Manager 100 table. The last name contains a not null and the hire date. An explicit not null specified in the table in our subquery is created in our new table. That is how we create a new table and insert rows at the same time by combining the create table and the as subquery option in our SQL statement. In this video, we will discuss how to change the definition of a table using the alter table SQL statement. After creating a table, you may need to change the table structure for any one of the following reasons. You may have omitted a column. Your column definition or its name needs to be changed. You need to remove columns, and you may want to put the table into read-only mode. These changes to the table structure can be done using the alter table statement. You can use the alter table statement to add a new column, to modify an existing column definition, to define a default value for a new column, to drop a column, to rename a column, and to change a table to a read-only status. We can add columns to a table, modify columns, and drop columns from a table using the alter table statement. The syntax for the alter table statement consists of the following. Alter table, we then include the table name, followed by the type of modification, add, modify, or drop. The column name is specified. We include the data type and the length of the column, and if a default value is to be specified, we specify the default value. In this video, we have described the reasons for needing to add, modify, or drop a column on a table, and we described the alter table syntax. Changing the definition of a table by adding, modifying, and dropping columns in a table using the alter table SQL command. The guidelines for adding a column to a table. You can add or modify columns. You cannot specify where the column is to appear. The new column becomes the last column. The example in this slide adds a column named job_ID to the dept80 table. The job_ID column becomes the last column in the table. Note, if a table already contains rows when a column is added, the new column is initially null or takes the default value for all the rows. You can add a mandatory not null column to a table that contains data in the other columns only if you specify a default value. You can add a not null column to an empty table without the default value. To modify a column definition by using the alter table statement with the modify clause. Column modification can include changes to a column's data type, size, and default value. Some guidelines when modifying a column. You can increase the width or precision of a numeric column. You can increase the width of character columns. You can decrease the width of a column if the column contains only null values, if the table has no rows, or if the decrease in column width is not less than the existing values in that column. You can change the data type if the column contains only null values. The exception to this is the char to varchar2 conversion, which can be done with data in the columns. You can convert a char column to the varchar2 data type or convert a varchar2 column to a char data type only if the column contains null values or if you do not change the size. A change to the default value of a column affects only subsequent insertions to the table. You can drop a column from a table by using the alter table statement with the drop column clause. Guidelines when dropping a column. The column may or may not contain data. Using the alter table drop column statement, only one column can be dropped at a time. The table must have at least one column remaining in it after it is altered. After a column is dropped, it cannot be recovered. A primary key that is referenced by another column cannot be dropped unless the cascade option is added. Dropping a column can take a while if the column has a large number of values. In this case, it may be better to set the column to unused and drop it when there are fewer users on the system to avoid extended locks. Note, certain columns can never be dropped, such as columns that form part of the partitioning key of a partition table or columns that form part of the primary key of an index-organized table. For more information about index-organized tables and partition tables, refer to the Oracle Database Concepts and the Oracle Database Administrator's Guide. We will now demonstrate how to use the alter table SQL command to add a column, modify a column, and to drop a column from a table. If the Manager 100 table does not exist, first create this table. In our script output, we can see our table has been created. We would like to add a column to our Manager 100 table. The statement to do this is alter table, Manager 100, add, and in brackets we're going to add the review_date column with date data type. Let's execute this alter statement. In the script output, we can see the table has been altered. Let's do a describe of our table. In the script output, we can see the review_date column has been added to the end of the table. Next, we would like to increase the size of the last_name column. To do this, we will modify the table. Our alter statement will look as follows. Alter table, Manager 100, modify, and in brackets the last_name column, and we specify the size for the column, varchar2 60. Let's execute this statement. Our table has been altered. Let's now describe this table. We can see in the script output that the size of our last name column has been increased to 60. Lastly, we decide we no longer need the column hire_date, and we would like to drop this column from our table. We will issue alter table, the table name, drop, and in brackets the column that we wish to drop. Let's execute this alter statement. In the script output, we can see our table has been altered. Let's do a describe on our table. In the script output, we can see that the hire_date column no longer exists in our Manager 100 table. You are now ready to change the definition of a table by adding, modifying, and dropping columns in the table using the alter table SQL command. Using the alter table set unused option to mark columns as unused. The set unused option marks one or more columns as unused so that they can be dropped when the demand on system resources is lower. Specifying this clause does not actually remove the target columns from each row in the table, and the disk space used by these columns is not released. The response time is therefore faster than if you executed the drop clause. Unused columns are treated as if they are dropped, even though their column data remains in the table's rows. After a column has been marked unused, you have no access to that column. A select star query will not retrieve the data from unused columns. In addition, the names and types of columns marked as unused will not be displayed during a describe statement. You can add a new column with the same name to the table as the unused column. The set unused information is stored in the dictionary view user_unused_col_tabs. The drop unused columns option on the alter table drop command removes all columns that are currently marked as unused for the table. You can use this statement when you want to reclaim the extra disk space from the unused columns in the table. If the table contains no unused columns, the statement returns with no errors. You can specify the online keyword to indicate that DML operations on the table will be allowed while marking the column or columns unused. The code example shows the use of the set unused column that sets a column unused forever using the online keyword. Note, the guidelines for setting a column to be unused are similar to those for dropping a column. We will make use of the Manager 100 table to demonstrate the set unused command for a column on a table. If this table does not exist, first create the table. Our table has been created. Let's describe the structure of this table. In the script output, we can see the columns that exist in our table. We will now set the review_date column to unused. To do this, we will issue the alter table Manager 100 set unused and in brackets the review_date column. Let's execute this statement. In the script output, we can see that the table has been altered. Let's describe the definition of this table. We are no longer able to view the review_date column for this table. Let's select from our dictionary view. In our dictionary view, we can see that there is one unused column in the Manager 100 table. We will now alter our table and drop unused columns. Let's execute our alter statement. Once this is completed, let's select from the dictionary view again. In our query result, we can see that there are now no unused columns for the Manager 100 table. In this video, we have covered using the Set Unused option to mark columns as unused when using the Alter Table SQL command. In this video, you will learn how to use the Alter Table SQL command to set a table to read-only. You can specify read-only to place a table in read-only mode. When the table is in read-only mode, you cannot issue any DML statements that affect the table or any select for update statements. You can issue DDL statements as long as they do not modify any data in the table. Operations on indexes associated with the table are allowed when the table is in read-only mode. Specify read-write to return a read-only table to read-write mode. Note, you can drop a table that is in read-only mode. The drop command is executed only in the data dictionary, so access to the table contents is not required. The space used by the table will not be reclaimed until the table space is made read-write again, and then the required changes can be made to the block segment headers and so on. Let's go to our SQL Developer session to demonstrate placing a table in read-only mode. Working with our Manager 100 table, we will set the table to read only. If the table does not exist, create it. Let's create our Manager 100 table. Next, we will set our table to read only by issuing the statement alter table Manager 100 read only. Let's execute this statement. In our script output, the table has been altered. Let us now attempt to insert a row into this table. When we issue the insert statement, we encounter an error, as no updates are allowed on this table. This is a read-only table. Next, let's alter our table to read-write mode. By issuing the alter table, Manager 100 read-write. Let's execute this statement. We confirm that our table has been altered, and if we then re-execute the insert statement, we can see in the script output, one row has been inserted. You now know how to use the alter table SQL command to set a table to read only. Using the drop table SQL command to delete a table from the database. The drop table statement moves a table to the recycle bin, or it removes the table and its data from the database entirely. Unless you specify the purge clause, the drop table statement does not result in space being released back to the table space for use by other objects. The space continues to count towards the user's space quota. Dropping a table invalidates the dependent objects and removes object privileges on the table. When you drop a table, the database loses all the data in the table and all the indexes associated with it. The syntax, drop table, we specify the table name and then optionally include the purge keyword. Some guidelines when dropping a table. All data is deleted from the table. Views and synonyms remain but are invalid. Pending transactions are committed. Only the creator of the table or a user with drop any table privilege can remove the table. Note, you can use the flashback table statement to restore a drop table from the recycle bin. We will demonstrate dropping two tables from our database. Before we start, let's create these tables. We will create the Manager 100 table and we create the departments_archive table. In the script output, we confirm these tables have been created. Looking now at the drop table statement. For our first example, we're going to drop the Manager 100 table. Let's execute this statement. In the script output, we can see Manager 100 has been dropped. As we had not specified the purge keyword, the storage consumed by the Manager 100 table is not released and the space is still assigned to the user's quota. Next, we are going to drop the departments_archive table. We will purge this table during the drop statement to recover the space used by this table. Let's execute the drop statement. In the script output, we can see the department's archive table has been dropped. You now know how to use the drop table SQL command to delete a table from the database. Now that you've learned how to create and work with tables using the data definition language, it is now time to put that knowledge to work. In this exercise, you will use the information in the table below to create the emp table. Save the statement in a script, execute the statement in the script to create the table, and confirm that the table is created. Next, you will modify the emp table to allow for longer employee last names and confirm your modification. For the next task, you will mark the dept_id column as unused in the emp table and confirm your modification by checking the description of the table. Lastly, drop all the unused columns from the emp table and then drop the emp table. When you are ready, pause this video and perform the exercise. When you are done, come back to the video and I will work through the exercise with you. In preparation for this exercise, as a first task, you need to create the dept table. Use the script provided to create the dept table. We will create our dept table now. In the script output, we can see the depth table has been created. For the first task, we needed to use the information displayed in the slide to create the emp table. We need to save the create script in a file. We need to save the statement in a script. We then need to execute the statement in the script to create the table and confirm the table is created. Our create table statement looks as follows. Create table, emp, the columns, ID column of data type number, length 7, the last name column of data type varchar 2, length 25, the first name column of data type varchar 2, 25, the depth ID column of data type number, length 7. We needed to include a foreign key constraint which references the depth table ID column. Let's save our script. We're going to save our script as create_emp. Next, we will open a new SQL worksheet window. To do this, we will right-click on the HR connection and select Open SQL Worksheet. From our new worksheet window, we're going to execute the create emp script. Let's execute this script now to create the table. In the script output, we can see the emp table has been created. Let's do a describe on our new emp table. In the script output, we can view the definition of our new emp table. For the next task, we need to modify the emp table to allow for longer employee last names and then confirm the modification. Our SQL statement looks as follows. Alter table, table name emp, modify the last name column, and we then include the data type varchar 2, and we've increased the length to 50. Let's execute this alter statement. Once the statement has completed, we'll do a describe on our emp table. In the script output, we can see the last name column length has been altered. The depth_ID column in the emp table is no longer required, and we need to mark this column as unused. We then need to confirm the modification by checking the description of the table. Our statement to set this column unused is alter table, emp, set unused, and our column name, depth_ID. Let's execute this statement. The table has been altered. Let's now do a describe on our emp table. In the script output, we can see that we can no longer see the depth_ID column. If we now select from the dictionary view, we can see that we have one unused column in the emp table. For the last task in this exercise, we first need to drop all unused columns from the emp table, and we then need to drop the emp table. To drop the unused column, we issue the command alter table, table name emp, drop unused columns. Let's execute this statement. Once the unused columns have been dropped, we can select from our dictionary view. The query result returns no rows. This means that there are now no unused columns in the emp table. Our last action is to drop the emp table. The syntax, drop table, emp. Let's execute this statement. Our emp table has now been dropped and no longer exists in the database.